Oh, hi, Christian. Thank you very much for joining the stream. Hello, everyone. So we will begin in a minute or so, just for waiting for people to join. Really excited about this one. Meanwhile, I'm just checking my Discord servers to see if there's any message I would like to reply to. Yeah, it looks like the information geometry stream got a lot of views, got many views. I don't know about. Honestly, I'm a little bit conflicted because I I honestly don't think I said a lot during that stream because I'm very much a newbie when it comes to information geometry. But I guess um, uh, a lot of people want to get into the field, right? I hope I didn't make too many mistakes in that video. So perhaps we should make a follow-up to see some concrete calculations. So anyway, let's get started. In this stream, we'll talk about and start to investigate stochastic processes in physics. So first of all, what's this little note I'm using? And actually, what is the prerequisite, right, for doing stochastic process in physics? I'm doing this series for the most part to reboot the now somewhat dormant stochastic calculus series. I'm not gonna lie, and hopefully this will help me find the motivation as well as how should I say the right amount of preparation to make a new stochastic process, a stochastic series. Because I was struggling. Oh shit, which direction should I go? Because right now we are in a stochastic series, right? If you go to the stochastic series playlist, I just finished discussing Brownian motion and heat equation. I was kind of struggling to decide, okay, which direction should I go? Should I talk about finance first? Should I talk about physics first? Should I talk about, I don't know, engineering first? With that set expectation in those direction, and it just kind of, I kind of got stuck. I'll be honest. And you know what? It's time to just get rid of that and start doing stuff. Okay, so no particular bias here because we will in the next few weeks or so we're going to rotate between those fields. And the thing is, stochastic process is is a lot similar. I mean, when it comes to literature, okay, the situation is a lot similar to tensor calculus and differential geometry. The thing is, mathematical literature and physics literature on the same subject has a very wide gulf, and to some extent, engineering literature too, but perhaps to a less extent. It is particularly noticeable in the physics literature because physicists uses a lot of things like the direct delta function and the Langevin equation. By the way, this guy is Paul Langevin, French physicist, whereas mathematicians very much don't use Langevin equation. So the notation, just the notation, the priority, the methods are different. So it can be rather confusing for beginners what to read and what you really need. Right? So that's what I'm talking about. So what is the prerequisite for this live stream, and in particular for this course written by Professor Matt Scott? Well, not a whole lot, just undergraduate probability. You need to know how to calculate mean and variance for discrete and continuous distribution. That's about it. And some differential equations. Okay, you need to know some differential equations, ordinary differential equation, partial differential equations, But once again, it doesn't have to be super in-depth. A first course in the subject would suffice. For example, you perhaps it's a good idea for you to have seen linear differential equations. And here we can see there's a PDE on the screen. This is the famous heat equation, aka diffusion equation. Right now, we are also on the channel starting to discuss PDE. Currently, we're on the subject of first order PDE, but definitely heat equation will be covered as independently. Okay, not as an episode in a stochastic series. Just heat equation itself deserves its own treatment. So that's the prerequisite, okay? Just differential equations plus probability, basic probability. Absolutely zero need for measure theory or real analysis. No need whatsoever, okay? So yeah, physicists don't take real analysis. We know that for a fact. I mean, not just kidding, okay? Many physicists are actually well versed in real analysis, but the thing is, we don't require it here, okay? So, so as a result, mathematically speaking, this is not very rigorous, quote unquote. But the thing is, mathematical rigor don't always correspond to physical reality. Mathematical rigor and physical rigor, aka modeling rigor, are very much different things. And it's one thing to have beautiful mathematics that are elegant, self-consistent. On the other hand, it's a different matter to have your model that work in reality or approximate reality in a sufficiently satisfiable way. Okay, so where do you get this note? It's in the stream link description. Actually, let me just go here. This is a bunch of reference for the subject. Here, this is Professor Matt Scott's homepage. He is a professor in the Department of Applied Mathematics at University of Waterloo. So his main area of research is mathematical biology. Yes, stochastic methods are very useful in mathematical biology or biophysics in general. Okay, in particular, if you guys seen in our PDE stream, we studied one example, that is continuous time birth and death process. That is a very common model in mathematical biology. Anyway, this is Professor Matt Scott's homepage, and if here, this is the link of the note. This particular link here. In the past, I have taught a graduate course in stochastic processes based on these lecture notes. Here, it's literally called little notes. And it's the same that we will look at today. Okay, so this is a primary material we will be using. It's very approachable. It is, it's a little bit over 300 pages, but it is not very dense. Okay, it is an introduction to the subject, not exhaustive, but it gets the main idea across and is very motivated. So I think people from physics background would like this. Okay. As well as as far as reference is concerned, the big one, okay, there are two, and in fact both were heavily referenced in these notes. One is Stochastic Methods by Gardner. Stochastic Methods by Gardner. Crispin Gardner, he is or was, I'm not sure if he is still alive, but he is a physicist from New Zealand, I believe. He worked in quantum noise, I believe. Yeah. So this book is the standard reference for stochastic methods in physics. A very famous book. It's got like well over 10,000 citations or something. So very influential book. Okay, and here, yeah, this is a book. And because it's a handbook, unfortunately, it does not have a lot of exercise. You can't use it as a textbook. It almost reads like a Russian textbook because Russian textbooks often don't have exercises because they put exercise in a separate volume. This is not the case here. That's the standalone book. Okay, it is a bit unfortunate that it doesn't come with exercise, but it has tons of examples. So that's very neat. And be sure to get the latest edition. Okay, be sure to get the latest edition. Earlier, I believe it is just called Stochastic Methods in Physics or something similar. Now it actually include some of the applications in natural and social sciences, in particular for finance. So yeah, I guess Professor Gardner recognized the demand of physicists entering the field of finance and added the finance chapter, which is pretty cool. So here are the content list. Hold on a second. There's no content list here. Anyway, it doesn't matter. Yeah, but anyway, this is a great book. Go ahead and check it out. And this one is slightly older. It's also a classic called Stochastic Processes in Physics and Chemistry by whom? By N.G. Van Kampen. So this one is older. It was first, I believe, came out in the 80s. This one has exercises, unlike the book by Gardner, but the exercises are tough. Okay, so it's unfortunate that there isn't many bridge level book. Okay, but perhaps Professor Scott's notes will play that bridging role here. So the notes by Professor Scott has exercises, and many of them are approachable. And the nice thing about Professor Scott's notes is that there is a quite extensive list of background knowledge, a review of classic probability, all right, and a review of mathematical methods, including some matrix stuff. This is linear stability analysis, ODE, some basic PDE methods, transform method, Laplace and Fourier transform, that kind of thing. Yeah, so there's that. But coming back to Van Kampen's book, this one is highly rigorous in the physics sense, because there's a lot of discussion over the validity of various approximations in physics, something you don't often see in more mathematically oriented textbook. All right, so if you look at classic textbook on stochastic processes from the mathematical side of things, chances are you will come across with a book like Doob, D-O-O-B, Doob. Doob was the inventor of the modern notion of martingale. Extremely rigorous book from a mathematical standpoint, but not always useful for physicists as far as direct application is concerned. Okay, so of course, in the same spirit, this series of streams are going to be very much applied and we're trying to make things as intuitive as possible, but that doesn't mean watering down the content, because as we'll see, the calculations are by no means trivial at all. Okay, solving the differential equations in this field can still be very, very challenging. All right, so enough for the resource recommendations. These two are standard references. Professor Scott's book will be, or notes would be our main material. And if you do wish to pursue the subject further, in the notes, I believe there are extensive extensive information on bibliography. Okay. Anyway, let's go to the main topic. So here today, of course, this is the first episode. We're going to be doing some actual math, but also at the same time discussing the historical or physical motivation, as well as just a little bit of a history, as you will see in the notes, how the dominant techniques in stochastic processes in physics came to exist. All right, let me go check up with chat. Wow. Okay, what does it mean by physical rigor / modeling rigor? Like, when does your math actually work? When does your math actually describe the physics process? For example, I made such an example earlier in one of my videos called "Is dx squared equals 0?" In physics, often you do the dx squared equals 0 thing. Kratas and Shrev, I know, right? That one is a classic, but for financial mathematics, it's pretty much useless for physics. Okay. I hated to break it to you, but Shrev is very much geared towards financial mathematics, and its use in physics and engineering is very much limited. Perhaps even more so in physics. I mean, I have the book by Kratas and Shrev. Ricardo, I believe you mean the book by called Brownian Motion and Stochastic Calculus, right? Yeah. Let me just search it up for you. Chad is very interested in that book. Indeed, it's a great book in its own right, but not what we're doing here. And for that book, you absolutely need to be a master in measure theory to even get started with. But that's not what we're doing here currently. Yeah. So this is a book by it's also a very famous book called Brownian Motion, Stochastic Calculus, written by Kratas and Shrev. This is extremely rigorous from a mathematical standpoint, but unfortunately, it is not useful, not very useful for physics and biology, and for chemists, biologists and chemists. Let's just put it that way. This is heavily geared towards pure mathematics as well as financial applications. Okay, so it is written for readers familiar with measure theoretic probability and discrete time processes who wish to explore stochastic process in continuous time. We do not assume any of such background here. Okay. Of course, we will do a non-measure theoretic based episodes on stochastic calculus, stochastic methods geared towards financial applications as well, but that comes later. Okay, we will discuss discrete time martingales, and of course we are currently on the channel weekly. There's a weekly series on measure theoretic probability, okay, based on Axler's book, and right now we're using two texts already, Axler and Ash. So not this one for this series. Okay. Okay. Hi Vernon, thank you very much for joining the stream. Good to see you. Just hi everyone for joining the stream. Okay, so there's that. This is a golf in the literature I was talking about. So if you show this book to, say, working physicists, they would not be able to, unlikely to make much sense out of it. Okay. They will be impressed by the mathematics, but they will struggle to relate to their field of research. That's the typical experience. Okay. So yeah, not this one, and probably not, well, to a less extent, I guess, the stochastic calculus for finance by Shrev. Shrev is the industry standard for mathematical finance. Stochastic calculus for finance, volume 1 and 2. So this one is a standard reference. Volume 1 and volume 2, this is great on its own. And in particular, you can start with volume 2 and use the 1 as a source of intuition. Okay. Oh, hi, Steve. Thank you very much for joining the stream. Oh, actually, there's a discount going on. Okay, I should consider getting the physical book. Anyway, coming back to the main topic here. So, let's just look at the objectives here. Professor Scott will describe this much better than I just did. This book is designed as an introduction to the ideas and methods used to formulate mathematical models of physical processes in terms of random functions. The first 5 chapters use in the historical development of the study of Brownian motion as their guiding narrative. Okay. Perhaps you should put we should put a plural behind it, because there are different approaches to Brownian motion. The remaining chapters are devoted to the methods of solution of stochastic model, because this is what physicists care about the most. Method of solutions. They don't always necessarily care about existence or uniqueness, right? Existence of a stochastic process in a functional space. They don't really care about that, but they do care about method of solution. The material is too much for a single course. Chapter 1 to 4, along with chapters 7 and 8, are ample for a senior undergraduate course offered to students with a suitably mathematical background. Familiarity with most of the methods reviewed in Appendix B. So currently at the University of Waterloo, there is a 4th year course on stochastic process based on these notes. So this is just to set the expectation straight. This is a level of a 4th year undergraduate course as well as a beginning master level course. Okay. For a graduate course, on the other hand, a quick review of the first 3 chapters with a focus on later chapters, which should provide a good general introduction to numerical and analytic approximation method in the solution of stochastic model. Okay. Numerical and analytic approximation method. This is basically the bread and butter in physics. You cannot do much physics without them. Okay. The content is primarily designed to develop mathematical methods useful in the study of stochastic processes. Nevertheless, an effort has been made to tie to the derivations, whenever possible, to the underlying physical assumption that give rise to the mathematics. So this is what I mean by physical rigor / modeling rigor. What's the physical assumption that gives rise to the mathematics? Does the math actually resemble physical reality? And here, actually, as a consequence, very little is said about the Ito's formula and associated methods of what has come to be called stochastic calculus. So this is not a textbook on stochastic calculus. Okay. Well, we did the Ito's formula, the most common forms, plural, in our video series, and I do hope to expand on that and give more examples. If that comes as a disappointment to the reader, I suggest these 2 books. Oh, actually, these 2 books. This one, Handbook of Stochastic Method by Gardiner. This is an old edition. All right, so this is an old edition. Get the new one I just mentioned. And this one covers stochastic calculus at a level of rigor suitable for average physics application. Oh, thank you very much, Steve, for your generosity. Seriously, thank you for being a channel member. Thank you very much for your donations. There's also a list of references in the book. They're usually pedagogical texts or review articles. A collection of exercises appear at the end of each chapter, and this is very helpful. I think these are exercises with a manageable level of difficulty. Some of the exercises in Van Kempen's book are very tough. So you also need domain knowledge in physics to do them. Some of those are meant to focus the reader's attention in particular points of the analysis. Others are meant to develop essential technical skills. None of the exercises are very difficult, and all of them should be attempted, or at least read. Okay, my hope is that the reader will find that the study of stochastic process is not as difficult as it's sometimes made out to be. Excellent, great promise. Okay, so yeah, acknowledgement, we'll skip that. List of content, introduction, very helpful historical review of how stochastic modeling in physics came to be. Second chapter, random process. Third chapter, Markov process. Markov process is perhaps arguably the most useful kind of processes in physics. Most valuable, most type of, so I can't speak English, the most useful type of, most useful class of processes in physics. Once again, this reflects the priority of the field, because for deterministic methods, so this is stochastic methods, right? This is stochastic method, but what's the most dominant deterministic method in physics? Well, ordinary differential equation and partial differential equations. Markov process is a direct generalization of ordinary and partial differential equations. So that's why Markov process is so helpful. And this is not true, for example, in finance. In finance, history matters, right? Markov process, the whole premise of Markov process is that the future depends on the current state only. Now, if you know the current state, then history can be ignored. That's the whole premise of Markov process. This is not particularly, not always a valid assumption in finance. Finance care about history, right? And perhaps not also very useful in statistics. In statistics, in particular in time series analysis, right? You use typically models such as the ARMA process. Now, those are generalization of linear regression in various ways. So it reflects the priority as well as the history of the subject. Markov process are direct generalization of differential equations, ODEs and PDEs. And those are the things, these are the common language among physicists. And they do a good job, or a reasonably good job, when it comes to modeling physical reality. So Markov process is going to be the key of what follows. Okay, so then we have the solution of the Masters equation. The Masters equation, once again, is a term that almost never appears in mathematical literature in stochastic processes, but is absolutely crucial for physicists. So what is Masters equation? In a nutshell, it is a restricted form of the Chapman-Kolmogorov equation with some special assumptions introduced. So that's the Masters equation. Chapman-Kolmogorov equation is the defining equation for Markov process, CK, and Masters equation is a special case. Okay, and perturbation expansion of Masters equation. So now we're talking about analytic approximation. Now, perturbation and asymptotics is on its own a very broad topic in applied mathematics / physics. A lot of useful solutions in physics are derived from perturbation assumptions, perturbation method. Once again, this is almost never ever discussed in mathematical literature. Seeing books like Shrev, they never talk about this, but it's useful in physics. Chapter 6, Fokker-Planck equation. And actually, this is something I plan to be the goal of the series, is to get to Fokker-Planck equation. Because right now we're also, as mentioned, doing PDEs. Fokker-Planck equation is an important class of PDEs. So this way we can see the connection between stochastic process and PDEs. Now, Fokker-Planck equation is typically mentioned in mathematical literature, however, under a different name, called the Kolmogorov forward equation. In mathematical literature on stochastic processes, quite often you will see Kolmogorov forward and backward equation. But depending on the specialization, they don't always make that the central object of study. Whereas in physics, Fokker-Planck equation is of paramount importance. Yeah, physics is basically mostly perturbation theory. That's completely true. But there's also non-perturbative, such as quantum electrodynamics is non-perturbative, which makes I don't know why I can't speak English tonight, which makes verifying quantum electrodynamics difficult because it is non-perturbative. 7, called stochastic analysis. So here we are actually introduced some kind of rigor into our discussion, like what we mean by saying a stochastic process is continuous, it is differentiable. What does Ito and Stochanovich integrals mean? Now, Ito's integral, here's a brief introduction. As promised as disclaimed, okay, in the preface, there's no extensive discussion on the Ito integrals or just stochastic calculus in general. Physicists like to do things with the Fokker-Planck equation, and not so much with Ito's lemma and etc. Okay, but it is mentioned here. Chapter 8, random differential equation, aka stochastic differential equation. The focus here is once again on approximation methods. Approximation method, including numerical simulation, which is also a form of approximation. Okay, and not mathematical generality. Chapter 9, Chapter 10 are more, and 11 are more specialized topics. Certainly uses perturbation theory, but it's not. I hate to go off a tangent way too far. But the series expansion in QED, quantum electrodynamics, are sometimes not perturbation series. So, like perturbation series, it's anyway. We'll perhaps tell what I mean if I have time later part of the stream. Would love to see your take on the Fokker-Planck equation. Thank you. Yeah, that's actually our central goal here. I wish to get to this minimum. Okay. So yeah. Actually, we have a diagram, very useful diagram in the notes. I forgot which page. Let me just try to find it. Okay, just to give like a big picture of, come on. No. Okay, so the relation between CK equation, Chapman-Kolmogorov equation, Masters equation, and Fokker-Planck equation. There's a diagram somewhere in the note. And in the meantime, you can kind of, at a very high level, see what kind of mathematics is used. Where is the Fokker-Planck equation? See, lots of differential equations, Fourier transform, that kind of stuff. And zero measures theory. Where is it? Yeah, right here. Awesome. This is the one I'm talking about. So you have the Chapman-Kolmogorov equation for a general Markov process. This is impossible to solve on its own. Okay, this is in general impossible to solve in full generality. And so you can specialize it for a stationary process. And then we introduce some extra assumption from microscopic theory to get the Masters equation. And then you get the Fokker-Planck equation. Okay, the Kolmogorov equation, or Kolmogorov's forward equation, yeah, I believe this is forward equation, is equivalent to Fokker-Planck. Okay, so there's that. So our goal is pretty much to explain this whole chain of deduction. Okay, awesome. There's a lot of interest, it seems. So let's get started without further ado, okay? So chapter 1 is very much a historical review of Brownian motion as well as stochastic modeling of physical process in general. 1.1 Stochastic process in science and engineering. Physics is the study of collective phenomena arising from the interaction of many individual entities. Even a cannonball dropped from a high tower would collide with some 10 to the 30th gas molecules on its way down. Part of the miracle of physics is that, as a rule, only a few variables are required to capture the behavior of the system. And this behavior can in turn be described by very simple physical laws. In the case of the following cannonball, for example, only its position and velocity are important. In hydrodynamics, despite the incredible number of individual fluid molecules, the flow velocity, density, and temperature are sufficient to describe the system under most circumstances. All right, so here Professor Scott is alluring to the fundamental PDEs for fluid dynamics, which will also derive in the PDE lives. Okay, usually it's some kind of conservation law. Yet the interactions that are eliminated from large-scale models make them felt in other ways. A ball of crumbled paper experiences a strong drag force in flight due to air resistance. So a constitutive equation must be provided to fix the viscoelastic property of the fluid, etc. Drag force, right, viscosity, electrical resistance. These are all vestige, I don't know this word, of the microscopic dynamics left behind in the macroscopic model, when the enormous degrees of freedom in the original many-body problem were integrated away to leave a simple deterministic description. Okay, so this is a rather difficult sentence. Basically what it says is things like drag, viscosity, basically stickiness in fluid, as well as electrical resistance. These are statistical phenomena. These are what's shown on a macroscopic level, basically on average of the behavior of, well, this many little particles. Okay, and sometimes these effects are significant. Vestige, a visible trace evidence or something that once existed but exists and appear to no more. Thank you very much. Yeah, thank you very much, Christian. So yeah, this is basically what we're getting to. And just as an example here, we did the birth and death process, remember? Here in our notes, or in the PDE. I don't expect everyone to follow all of my stream. I mean, this is impossible, but just as a brief remark of what Professor Scott is saying. So at a microscopic level, to describe a population growth or just evolution, we can use the birth and death process, because it models the individual growth and death rate. Okay, and the result, of course, is a stochastic model, and you have the Kolmogorov forward equation to describe the evolution of probability distribution. Okay, but let's say if you're just interested in the average behavior, what do? Well, essentially you perform an integration. You perform an integration to get the differential equation for the mean. And what's the result? Here, the mean evolves according to the simple exponential growth differential equation. M dot equals a constant times m. And that's, of course, the classic exponential growth model. So this is what Professor Scott means. Okay. So sometimes the randomness, the statistical nature of the phenomenon is obscured by a deterministic model. And for example, say in the continuous time stochastic model, you can talk about things like when do the population go extinct, because that's a possibility. But in the deterministic equation, it's impossible to tell. As m follows exponential growth or decay, it can only grows to infinity or decay to zero, but it never actually truly reaches zero. So you cannot get information on saying when do the process actually go extinct, or the probability for that happen. It's simply not in this model. Stochastic method allows us to discuss those behavior. Okay. Yeah. All right. So yeah, that's an example here. These shadows of microscopic motion are often called fluctuations or noise, and their description and characterization will be the focus of this course. Deterministic models, typically written in terms of system of ODEs, have been very successfully applied on an endless variety of physical phenomena, for example, Newton's law of motion. However, there are situations where deterministic laws alone are inadequate, particularly as the number of interacting species becomes small, and the individual motion of microscopic bodies have observable consequences. Okay. Oh, by the way, there's no assumption that you already know quantum physics in this series. No. Okay. So when we say microscopic, we mean at a scale that is still valid to use Newtonian mechanics, but the influencing forces have too much fluctuations that the solutions fail to be smooth, if that makes sense. So you don't need to fundamentally change the law of physics here. For Brownian motion, you don't need to use quantum mechanics. Okay, Newton's law of motion still very much applies. It's just the number of degrees of freedom is so large that solving Newton's law becomes impractical. Okay, so that's kind of a disclaimer of what we're doing here. We're not discarding Newton's law of motion here. Okay, we're just applying it on a scale that is usually not done for typical application of classical mechanics. However, there are situations where deterministic laws alone are inadequate, particularly as the number of interacting species becomes small and individual motions of microscopic bodies have observable consequences. But still, no need for quantum mechanics in this series. You can introduce quantum mechanics, for example, in Gardner's text into the equation, but we're not doing that here. Yeah, the pollen grain is very much a classical system, exactly. But it interacts with such a large number of molecules that the Newton's law becomes impossible to solve. All right, the most famous example of observable fluctuation in a physical system is Brownian motion. The random, incessant, is this pronounced meandering? Guys, help me out here. English not my first language. Meandering? Incessant meandering, basically moving around, of a pollen grain suspended in a fluid, successfully described by Einstein. Okay, no worries, no worries. So I'll try to make my expositions, so to say, not too quickly, because I mean there's no deadline for us to catch here. You can kind of just chill, listen to this as a podcast even until when we get to actual derivation. Okay. So the next major developments in the study of noise came into the 1950s and 60s through the analysis of electrical circuits and radio wave propagation. Yeah. And also this is the golden age of control theory. So there was huge breakthrough in the 1950s and 60s when it comes to stochastic control, which will be, well, in separate episodes for engineers, stochastic methods for engineers. Today, there's, again, renewed interest in the study of stochastic processes, particularly in the context of microfluidics. Interesting, I don't know what that means. A nanoscale devices and the study of genetic circuits that underlie cellular behavior. I guess this is Professor Matskall's research. Chad says, interesting to note, thinking out loud, Yeah, go ahead. This is me thinking out loud. Okay, go ahead, please think out loud in chat. That even if we take the system as being Newtonian, the random components of a model aren't actually computable, is that right? I can't compute the actual realization of a random process. Yes. Yes. And the thing is, let's say if you are able to calculate the trajectory of the Brownian particle, how does that connect to our observation, right? How does that sort of say, convert to the quote-unquote useful properties of the system, right? So let's say, imagine you have a supercomputer that allows you to calculate the trajectory of the Brownian particle, allows you to solve deterministically, okay? You have the information of all the forces involved. Like, what good does that do to you? For example, I want to know the temperature or the pressure of the system. This is very much stochastic, not stochastic, but statistical mechanics. Right? The problem with statistical mechanics, I want to know the pressure of the system. I want to know the temperature, because these aren't variables available in the microscopic laws. Okay, so once again, I'm not going to make this into a series of statistical mechanics either. Basically, no domain knowledge of physics is assumed. The subject matter is purely on stochastic process. We will discuss some motivation from physics without doing actual physics. Okay, they just want to set the expectations straight. And if you want to see actual physical applications, go check out the two references I mentioned earlier. So these are written by actual physicists. In particular this book by Van Kampen, and to a great extent as well by Gardner. They're very readable books. If you know differential equations, then these are very readable books. But they're still not very easy. Definitely both are graduate level texts. Okay, anyway, here, let's continue. So here, why study Brownian motion? Brownian motion will play a central role in the development of the ideas presented in these notes. This is partly historical because much of the mathematics of stochastic processes was developed in the context of studying Brownian motion, and partly pedagogical because Brownian motion provides a straightforward and concrete illustration of the mathematical formalism that will be developed. Furthermore, Brownian motion is a simple enough physical system that the limits of various assumptions employed in the modeling of physical phenomenon are made obvious. Okay. Awesome. So, I think it's fair to say most of the mathematics come from physics. Not all, but most of the mathematics come from physics. Or if we want to restrict that statement and say most of the applied mathematics came from physics. 1.2, Brownian motion. Using a microscope, Robert Brown, who's a botanist, by the way, not a mathematician, not a physicist, but a botanist. Robert Brown observed, in the 19th century, observed and documented the motion of large pollen grains suspended in water. No matter Brown did, the pollen grains move incessantly in erratic and irregular motion. Here's a picture. The funny thing is, when this was first observed, it was considered, it was postulated or cited as evidence for the difference between organic and inorganic matter. Organic matter are those, quote unquote, are capable of giving life. But the problem is, soon it was observed that even dead pollen grains have the same behavior. So it must have nothing to do with life. Okay. This sort of irregular motion was initially considered for a short period as evidence of the distinction between organic and inorganic matter. but quickly it was dismissed. And it turns out that in modern chemistry, there is no hard boundary between organic versus inorganic matter. Okay. Anyway, here, Brown tried different materials and different solvents, and still the motion of these particles continued. Now, this was a time when most scientists did not believe in atoms or molecules. So if you guys know a little bit about the history of physics, atomism was still very much viewed with great suspicion in the middle of the 19th century, and physicists who, like Boltzmann, who based their foundational work on that assumption, experienced great resistance in academia. People just did not believe atoms or molecules, or shall we say, have doubts about whether these things existed. All right, so in the words of S.G. Brush, 3/4 of a century of experiments produced almost no useful results in understanding of Brownian motion, simply because no theorist had told experimentalists what to measure. All right, so this is a sample pass. Okay, A is a sample pass of the Brownian motion. B is the schematic of the physical mechanism. So basically, you can consider the pollen grain as this big ball. It's been bombarded by numerous particles. Okay, this little diagram is on the thumbnail of the stream. All right, so notice the figure is not to scale. In reality, it would be about 10 to the 9 solvent molecules in the view shown. And each molecule would be about 1/100 millimeter in diameter. So the scale is very much exaggerated. The pollen grain is still much, much larger than the molecules. Okay, and by Brownian motion here, we refer to the sample pass of the pollen grain. Now, this is not the trajectory of molecules. That's quite often a great misconception. The trajectory, this observed trajectory, is the trajectory of the pollen grain. After all, this was observed in the middle of the 19th century. Right? Individual molecules aren't really visible until the 20th century. Okay, so thanks mainly to the work of Gouy, how do you pronounce his name? I don't know. But anyway, several suggestive facts were known by the century's end. Okay, these are important. These are very important because the mathematical formalism has to reflect these observations. Otherwise, they're just fun math, not very useful math. Okay, the motion of particles is very irregular. It's very irregular, actually. And the path appears to have no tangent at any point. That is basically, it is nowhere differentiable. Although, of course, it is continuous. So you see, this kind of parallels the development analysis. Because this was observed in the 19th century, in the middle of the 19th century, or earlier part of the 19th century, I'm not quite sure. But that was also the time when rigorous calculus, quote unquote, or real analysis or complex analysis together were developed. Right. So mathematicians initially believed there is no such thing as a non-differentiable function, a nowhere differentiable function. People like Cauchy initially believed that a function can only be non-differentiable in, basically, in today's term, a countable set. And he attempted to prove such things, which of course, those proofs are false because the statement is not true. Right. So it was later that I think Weierstrass introduced the first nowhere differentiable function. Okay. Let's go check out the picture here. Weierstrass function, historically the first nowhere differentiable function, but still continuous everywhere. It was a purely mathematical construct in the form of an infinite series. So this is Weierstrass' definition. It's a trigonometric series. So the idea is you can capitalize on the oscillatory nature of the cosine function, trig function, and make the oscillation infinitely frequent. So you get this structure. This is a continuous but nowhere differentiable function. And historically, this is a great shock to mathematicians. I believe Henri Poincaré called this an assault to common sense. In his opinion, in Poincaré's opinion, European mathematics have gone too far into obsessions with constructing counterexamples and not paying attention to physics anymore. And quite ironically, in the same period, Brownian motion was discovered. These are nowhere differentiable functions in nature. So these aren't just mathematical pathologies. Okay, functions like the Weierstrass function is not just a mathematical curiosity. They appear in physics. Okay. The particles appear to move independently of one another, even when they approach closely. Okay, so the independence assumption. Or no, this is actually not an assumption, but this is actually an observation. Quote unquote suggestive facts. Point 3. The molecular composition and mass density of the particles has no effect. Interesting. So, yeah, these are things that aren't relevant. Molecular composition as well as mass density aren't related to the Brownian motion. Okay, as the solvent viscosity decreased, viscosity, basically the stickiness, viscosity decreased. So it's like going from olive oil to water. You change the solvent from olive oil to water, viscosity decrease. The motion becomes more active. So it's kind of intuitive, right? Less resistance. Viscosity is basically the notion of friction in fluid dynamics. Part 5. As the particle radius is decreased, the motion becomes more active. 6. As the ambient temperature is increased, the motion becomes more active. I think this is also quite intuitive, right? So imagine you have a bag of tea, and you pour cold water versus hot water on top of it. Based on our common sense, if you pour hot water on top of it, boiling water to a tea bag, the solution quickly turns to whichever color the tea bag is supposed to be. Right? So, whereas for colder water, such transition happens slowly. And also, lastly, the motion never ceases. So, this is the state of affairs when Einstein published his seminal paper in 1905. Actually, 1905 was something Einstein himself called his miracle year. So this is also very interesting phenomenon. I mean, just history. It's history of physics. Einstein's miracle papers. And the thing is, Einstein published, because before he was kind of struggling to find a job, to get recognized. Right. Einstein's miracle years, or in Latin, annus mirabilis papers. So he published 3 papers that year. The first one is on photoelectronic effect. This was the dawn of quantum mechanics. Second is the one on Brownian motion. I believe we will see a passage of that today, translated version today. It's included in Professor Scott's notes. Okay. Which he established Einstein relation. We'll see, likely we'll see how this relation is derived by Einstein. And this is the deal that sealed atomism. So atomism is no longer just a fringe minority in the physics community. It compelled the physicists to accept existence of atoms. So this is very, very significant. And the third one has to do with special theory of relativity. And the fourth one has to do with special relativity, but in this case, it is the dynamical consequences. So the third one is explains the kinematics of relativity, the Lorentz transformation, velocity addition rule, such things like that. And the fourth one is about the dynamical consequence, including the famous equation E equals mc squared. all done in 1 year. So, yeah, miracle indeed. So coming back here, we have the miracle paper. We'll take a look at part of it as mentioned. So Einstein, this was the state of affair when Einstein first published his paper on Brownian motion. And the state of affair compelled him to write in the opening paragraph of the article that it is possible that the movements to be discussed are identical with the so-called Brownian molecule motion. However, the information available to me regarding the latter is so lacking in precision that I can form no judgment in that matter. Okay, so yeah, imagine doing research without Google. Pretty incredible stuff. A combination of genius, hard work, and luck, I believe. So, Einstein's argument is a classic, and it contains the seed of all of the ideas developed in this course. Yeah, saved a few more books from AI books burning today by buying old books. Anyway, to appreciate the revolutionary nature of Einstein's formulation of the problem, it is important to recall that at the time, many physicists did not believe in atoms and molecules. The argument is built upon two key hypotheses. All right, so here we might need to take some notes here. Einstein's argument on Brownian motion. Two key hypotheses. First, that the motion of the particle is caused by many frequent impact of incessantly moving solvent molecules. Basically, this diagram here. That's the first assumption. Okay. Second, that the effect of complicated solvent motion can be described probabilistically in terms of very frequently statistically independent collisions. Okay, so sure, let's put that down in our notes. And just to save some time, I'll just do a screenshot. It's always nice to have some sort of open source material. I can just take screenshots instead of writing all these words on my notebook. If this is a copyright book, I have to do that myself, which will of course cost time. So yeah, this is Einstein's argument. 1905 paper. Oh, I need a new notebook. This is getting too big. Okay. So Einstein's paper, 1905. On Brownian motion, 1905. Statistics is a weakness of mine. I mean, you don't need advanced statistics to follow this series. Just basic probability will do. Yeah. The definition of mean and variance, like conditional probability, all at a non-measure theoretic level, is perfectly adequate. Okay, sorry, let me just drink some water. All right, Einstein's approach follows two directions. Okay, this is perhaps also important to put in our notes. The first is physical. Balancing the, hold on a second, is that even a word? Osmotic? Balancing the osmotic pressure with the body force acting on the particle, Einstein derives a PDE for the particle density. So what do we mean by that? We will see it here. I mean, just perhaps, yeah, we will see it here. This is the original excerpt. I mean, not the original, but the translation. The excerpt from Einstein's, as in osmosis. Okay, still, I have no clue what that means. Anyway, here we have the first central result we wish to derive, that is the heat equation or diffusion equation. Okay, this is in fact the prototype of the Fokker-Planck's equation. The Fokker-Planck's equation in general is a what we call a parabolic PDE, PDE of the parabolic type. That is to say, it has second-order partial derivatives with respect to the spatial coordinate, and the first-order partial derivative with respect to the time variable. Okay, that's the general situation. In general, you also have a drift term on the right-hand side. That is basically df over dx, the first-order partial derivative, the drift term. Okay, so here there's no drift term here. That's the diffusion equation. We will see Einstein's argument for it. Here, the diffusion coefficient d is a measure of how quickly the density distribution will spread along the x-axis. Okay, so you can think of purely basically mathematically, just purely mathematically, without looking at the physics. How do we interpret this equation? We can do it this way. So let's think about the function f, the density. F is a probability density as a function of x only. Okay, where t is a parameter. So I'm treating f of x and t as a function of x parameterized by t. So t is a secondary variable. X is a primary one. Okay, so initially, say the position of the Brownian particle is at x naught. So because you know initially where the particle is, the density at initial time is just a direct delta. It is completely concentrated at this point. You have 100% certainty. And now as time evolves, it becomes less and less, so to say, it becomes less and less accurate. The information about the position become less and less accurate. So as you can imagine, the distribution will spread out like that. But what is the rate of such evolution? Well, it says it is proportional to the second order partial derivative, but we know what this is. Second order partial derivative is a measure of curvature. Say at a certain point, the distribution is like this. Okay, so this is t equals 0. This is what happens when t is positive. This is a new density profile. Okay, so for example, at this point, say x, consider a fixed coordinate. If you just like focus your observation at this particular time, you want to take a look at how the density evolves. Okay, the same position. Let's put x here. Originally at x there is no particle whatsoever because, well, it's concentrated at one point. And now you have a non-zero probability of observing the particle at this position x. Yeah, how does the probability density evolve? Well, it is proportional to the curvature. d squared f over dx squared is the curvature of the curve. Linearized curvature at the point. So basically it says if a curve is more concave or convex, then the evolution of the density at that point is faster. So that's the interpretation from a pure calculus point of view of the diffusion equation. Okay, so basically think about it. So when does second order derivative equals 0? Elementary fact from calculus. It happens when f is a straight line. When f is linear, say ax equals b, then the second derivative vanishes. So there's no curvature. No curvature, no time evolution. Right? So that's the idea. Okay, so that's the qualitative description of the diffusion equation. So the probability density will be shown to be governed by this PDE. All right, the d is the multiplicative constant. Okay, and so that's the first one, I guess. Is that the first one? Okay, actually that's the first one is still going on. This is the second one. Continue. For a spherical Brownian particle with radius r, using Stokes' theory of the drag force acting on the particle. So the Stokes' theory says for low random numbers, the drag force is proportional to a bunch of variables, linear in the diameter, I believe, and also linear in the velocity. We'll see details about that later. Okay, using the Stokes theory for the drag force, which is well accepted at the time, Einstein derived the diffusion coefficient. So the diffusion coefficient, just based on this result, right, we can see what's going on. The diffusion coefficient, d, is kb times t over 6 pi nu r. T is the temperature, so d is proportional to T. The higher the temperature, the larger the diffusion coefficient. So basically, the stronger the diffusion effect is, right? And the smaller the R is, the bigger the D as well. So these two qualitative assumptions, these two qualitative behavior of this result is consistent with the observation earlier. As temperature increases, the motion becomes more active. As the particle radius decreases, the motion becomes more active. Okay, and as well as the viscosity, nu here is the viscosity. Nu appears in Stokes' theory of the drag force. So nu is the viscosity. If the viscosity increases, decreases, if the viscosity decreases, the diffusion is also more pronounced. So this is a major result. Here, nu is the shear viscosity of the suspending liquid. T is the absolute temperature. Kb is Boltzmann's constant. The units of Kb are such that kBt has a unit of energy. Knowledge of the value of Kb is equivalent to the knowledge of Avogadro's number. I mean, if you're a physicist, this is well known to you. And hence of molecular size. Notice how the qualitative aspect of Brownian motions are reflected. Earlier we seen that, right? Are reflected in this expression for the diffusion coefficient. How d changes according to the changes in the variables t, nu, and r. Very interesting. Okay, so that's the second direction. So let me just give a quick summary of the first direction. Okay, so here, what are the outcomes here? Results. So the first result is quote-unquote physical. To go from physics, you get the heat equation or the diffusion equation, dF over dt equals d square f over dx squared. And using the Stokes drag law, the same guy the same guy in the theorem, Stokes theorem, in vector calculus. Stokes, British mathematical physicist. Stokes drag law. This works for fluid with high viscosity and particles moving at slow speed, essentially. Stokes drag law. We will talk more about drag laws, in particular aerodynamic drag laws, in the ballistic series. So the Stokes drag law is d equals kb times t 6 pi nu r. So basically, d increases, more diffusion, stronger diffusion, stronger Brownian motion, stronger diffusion. If higher temperature, smaller radius, or smaller viscosity. So nu is called the shear viscosity. Here, so nu is the shear viscosity of the suspending liquid. Okay, and let me just draw the picture. This is R, the radius of the pollen grain, and you have a bunch of Brownian particles that bombard it. Okay, bounce right off. That's the situation here. Okay. So that's the first result. The second direction of Einstein's paper is mathematical. Using the simple assumptions to derive a PDE governing the probability density of finding the... Hold on a second, that was supposed to be physics. Balancing the osmotic pressure with the body force. Oh, actually you can derive it from physics as well. Oh, I didn't know that. Okay, interesting. Basically there are two ways to... Einstein gave two arguments to derive this equation. I didn't read the whole thing, so maybe I should. I didn't read the full paper of Einstein. It's of course freely available, and as far as I can tell, the mathematics is not very involved. Just basic second year level of mathematics and physics should be enough to understand Einstein's paper. I should really read it. So basically here it says balancing the osmotic pressure with the body force acting on the particle. Einstein derived the PDE. But here you can also derive the PDE purely mathematically, using simple assumptions to derive the same PDE using the probability density. Hold on a second, that's not originally the density? I thought this is meant to be the density. Particle density, what does particle density mean? Does that mean the density of the Brownian, not the Brownian particle, but the molecules? Okay, we'll have to see about that. Because I've taken this course many years ago. We'll see what this really means. Okay, but here the second direction, perhaps this is more familiar. I used pretty much an equivalent formulation in my video on Brownian motion. Okay, and it was done purely probabilistically, with no physical assumption whatsoever. For example, I did not introduce this equation for D. Instead, I derived the heat equation purely probabilistically, using a discretization argument, which is equivalent to the second direction that Einstein took. Okay, so the PDE governs the probability density of finding the Brownian particles at a given position x after time t. The derivation will be echoed throughout this course. Okay, so the PDE is the same, but the interpretation is different, it seems, compared to the first approach, which is quite interesting. The original article is a wonderful piece of scientific writing, not only because of the historical significance, but because of the clarity and the force of central ideas. For that reason, the proportion of the paper describing the derivation of the PDE is reproduced as below. Okay, so let's summarize it here. Here F is the particle density. Particle, aka molecule density. Question mark? I suspect this is what it means. And the physics involved is, quote unquote, balancing the osmotic pressure by osmotic pressure balance. Okay. This could be an interesting piece of writing, so to say, as a tutorial. So how do Einstein get the diffusion equation in two ways? Okay, let me just underline this because I don't understand that. Second is purely mathematical, just from probabilistic assumption, probability laws. It also gets the diffusion equation. Here, let's write it dp over dt, okay? dp over dt, where p is the probability density. Okay, p of x and t equals the probability density of big X, the position, x say xt, the position, which is random, the random position of the of the pollen grain. So that's the law of probability. And we will see how Einstein got that equation. This is a crucial derivation because this is essentially how we get the Fokker-Planck's equation in a general case. Excerpt from Einstein's paper on Brownian motion, author's translation. Here, it must clearly be assumed that each individual particle, namely the solvent particle, water, oil, whatever, the solvent particle, executes a motion which is independent of the motions of all the other particles. It will also be considered that the movement of one and the same particle in different time intervals are independent processes. Okay, so let's draw a picture. So let's say this is the trajectory of one particle. This is going from t from t0 to t1. Okay, so this is one trajectory, and here you have a second trajectory. Okay, not a smooth trajectory, yeah, but another trajectory of a separate fluid particle. Okay, fluid particle, not the pollen grain. Okay, these two are assumed to be independent processes. Oh, hang on. Yeah, that's the first assumption. This is the before the semicolon, right? So different particles, they move independently. And also, even for the same particle, if you just concentrate on one trajectory, say this part of the trajectory is independent to this part of the trajectory. These are also independent. As long as the time intervals don't overlap, as long as the time intervals aren't chosen too small, then they can be considered independent. So this is a physical assumption. It all has to do with the scale. Okay. So the idea is, statistically speaking, this is basically the application of a central limit theorem. Over each time interval, we want the time interval to be long enough that it is the resulting trajectory is the effect of a combination of numerous factors. Now this way, the central limit theorem can be applied. So that's the physical assumption here. The time intervals cannot be too small. We introduce a time interval tau into consideration. So this is a small time interval, tau, which is very small compared to the observable time intervals. Right. So it's like if this is a complete trajectory. Here earlier there was a diagram for the complete trajectory. Right. The complete trajectory takes in the observable time interval, and you're just considering a small fraction of it. Right. Over that time interval, say tau, what happens? Okay, here, this is a small time interval tau, just small compared to the observable time intervals, but nevertheless so large that at two consecutive time intervals, the motion executed by the particle can be thought of as the events which are independent of each other. Okay, interesting. So that's the physical assumption of this derivation, tau. Okay, the tau is small compared to the observable time intervals, but nevertheless it is still very large, so that you can make the independence assumption. So basically the effect of the previous time interval is no longer felt in the second time interval. Very important physical assumption. Now let there be, okay, actually I'm actually going to put it down here, because this has to do with very important interpretation of the model. Einstein's paper, the time interval argument from Einstein's paper. So the independence assumption comes from the time scale. Is based on time scale choice. Not too small, not too large. Okay. Once again, why do we need that? Well, to simplify mathematics. You can use the law of probability. Yeah, it is a Markov assumption, yes. Sorry guys, I haven't been reading chat. Let me catch up with chat. In a distribution of particles moving along Brownian paths has particle density, so finding particle units per volume. Yes, here we're finding particle number of particles per volume. We are doing that. Probability doesn't link about any underlying masses, just probability. So that's the Markov assumption. Yes, this is a Markov assumption. This is in fact perhaps more accurately described as the independent increment assumption. Independent increment assumption. So basically it says, say, if you have a process xt, right, and here you have interval S1 to S1 to T1, and this is S2 to T2. They have no overlap. As long as the the time intervals, if they don't overlap, then the delta xt1, okay, delta the first increment, so to say, basically x, let's write it as xt1. The increment here, xt1 minus xs1, is independent of the second increment. This is the independent increment property. Although I think it is also implied by the Markov property. I think it is implied by Markov property. Markov property basically says if the present is known, then the past is forgettable. Okay. All right, so now let there be a total of n particles suspended in the liquid. That's the total particle. That's the total mass, basically. Total of n particles suspended in the liquid. In a time interval tau, the x-coordinate of individual particle will increase by amount delta. For each particle, delta has a positive or negative value. So imagine if diffusion only happens in one direction. So this is x, okay? This is the x direction. In fact, let's use big X. So big X coordinate, the particles, they move randomly on the x-axis, and each individual particle through that time interval, during that time interval, travels a random quantity, delta. Okay. This is an incredibly large number of particles. Each will make its own move in the time interval. And delta, of course, is a random quantity. Right. So we can only describe delta. I mean, this is my own interjection, okay? So because delta is different for a large number, each delta is different for a large number of particles, you can only aim to describe delta statistically. So this is where the next sentence comes into play. So yes, Markov processes are from 1906. Einstein did not think in terms of them, but his physical intuition is, of course, spot on. Exactly. And of course, mathematically, as we will see, Brownian motions are Markov process. Okay. Brownian motions aren't stationary process, but they are Markov process. Okay. Brownian motion is Markov and Gaussian, but it's not stationary. Anyway, here, continuing with Einstein's original paper, here it says there will be a certain frequency law for delta. What does that mean? Basically, this is a probability density statement. The number dn of particles, so dn out of n is the total number of particles. So number dn of particles which experience a shift which is between delta to delta plus d delta will be expressed in the expression of this form. So dn is what? dn is the number of particles who makes a displacement between delta and delta plus d delta. Okay, so so some particle may move by a large distance, some particle may move by a small distance. These are all possible. But now let's consider just the number of particles whose shift is between delta and delta plus d delta. We assume it takes the following form. So basically that's the probability density. Remember, dn is the number of particles, so dn over n is the probability. dn over n is the probability for the particle to move between delta and delta plus d delta. And it turns out to be what? And I mean, not turns out, but assumed to be what? Assumed to be, this is the probability, so it can be expressed as a probability density times the change in the random variable size, d delta. Okay, that's exactly how we introduce continuous probability in elementary probability. Right? So that's the fraction of, think about for example, the income distribution of a general population. Right? Then you have a density. The income is a continuous variable. I suppose this is the income distribution. Right? Then for, say, a small interval on the income axis, x to x plus dx, right? The area underneath the density in that small interval is the fraction of a population whose earning is in that bracket. And of course, it's just the density times the dx. This is exactly what it says here, just for Brownian motion. Okay, so where the integral of phi is 1. This is, of course, the normalization condition in probability. So we are assuming what? Once again, let's rephrase this once again. What does this say? It says that the probability for the particle to move between delta and delta plus d delta can be expressed as a density function phi times d delta. That's it. And another physical assumption is that phi is only different from 0 for very small values of delta. Okay, once again, great physical intuition here. The idea is, because the interval isn't very long, right? It's small compared to the overall observable time interval. Here, going back to the picture, we're only considering a small time interval so that only a small displacement can happen, statistically speaking. This way, the function phi should only be non-zero for small values of displacement. And we also assume symmetry, because there's no reason to assume that the motion is biased in any direction. Right, so the density should be an even function. So this is phi. It's highly concentrated near 0. Right, so the overwhelming displacement is small in that time period, and it shouldn't be it shouldn't bias towards left or right. Basically, it should be an even function. That's the physical intuition here. Yes, should it be, yes, dn over. Thank you very much for the gift, San. Thanks very much. Much appreciated. So dn equals n approximate, yes, of phi delta. But basically, in an infinitesimal sense, you can write equal. So it's like if you want to write this as a derivative, right? Then the dn over n, okay, over d delta should be phi of x. Should be not phi of x, phi of delta. Yes, this is an approximation, but well, you know the drill. In infinitesimal sense, it becomes an equation. Okay, so that's the assumption on the probability density. Very, very important assumption, because later on we will do integrals and certain term will cancel, certain term becomes 1, things like that. Okay, so bear in mind what this means. So you see how the small interval assumption comes into play here? The interval is small compared to the overall time intervals, so that you can say things like, oh, the motion is unbiased, right? And also the overwhelming transition should be small. The overwhelming position transition should be small, concentrated near 0. Okay, that's the small part of the physical assumption, but it also is very large compared to what? It's also large so that you can apply independence. You can think of independence movement. So this is a very delicate choice of delta, not delta t. Anyway, let's continue. We now investigate how the diffusion coefficient depends on phi. Okay, how the diffusion coefficient, big D, depends on phi. We shall once more restrict ourselves to the case where the number nu of particles, okay, this is nu, it's not the viscosity, okay, this is a nu. The number of particles per unit volume, depending on x and t. Okay, so once again, this is only 1D motion, basically, it says. The number nu of particles per unit volume depend only on x and t. Okay, so here we're considering, oh, by the way, this is different, right? So this is different from phi. Nu equals f of x and t, this is different from phi. Phi is what? Phi is the distribution of the displacement. Remember what delta is. Delta is the displacement made by individual particles during that time period, tau. You see, each the x-coordinate of individual particle increased by amount delta. This is very clear. So this is a distribution of the jump. Delta is a random jump. Phi of delta is the PDF, probability density function for the jump. And here we define a new quantity, nu. Nu equals f of x and t is the number of particles per unit volume. So that's, I believe, here the particle density is about. See, f this is nu. The number of particles per volume. This is what it means. Okay, so coming back here, what can we say about this? What can we say about this? So we compare the distribution of particles at the time t plus tau from the distribution of time t. Right? So distribution of particles is basically a histogram. And now, I mean, you're considering it as a continuous function, not as a literal step function. Right? So this is a density function, f. So this is one distribution, and this is what happened at the small instance after. So the first curve is at time equals t. Yeah, just time t. Time equals t. And the red curve, the red distribution, is what happens after a small time interval. So this is time equals t plus delta t. Not delta t, but tau. Okay? So we want to compare those two densities and see how they're related. Okay. From the definition of the function phi of delta, remember what is phi of delta? Phi of delta is the density of the jump, the probability law of the jump. It is easy to find the number of particles which at time t plus tau are found between two planes perpendicular to the x-axis and passing through the point x and x plus delta x. Okay, so once again, back to the physics again. This is the x-axis here. This is the x-axis, and Here, let's draw two planes. This is at position x. This is at position x plus dx. Okay. So originally, what is the number? Actually, here we're considering the number of particles in this volume, in this one-dimensional volume, at the new instance. And that equals the left-hand side, obviously. Okay, I'll rechat in a bit. I'll explain this important equation. This is crucial here. Probabilistically speaking, this is basically the law of total probability. This is basically the law of total probability, but let's give a physical argument for that. So this is, the left-hand side is the number of particles within the interval t x plus d dx at the new time. So time goes from t to t plus tau, right? So at this new time instance, the number of particles that falls into this volume is the left-hand side. But how does this connect? Right, so to say, how does this connect to the previous instance? How does this connect to the previous instance? Well, you might have particles moving in and out during that time period, moving in and out of this volume during that same time period. And we wish to justify the right-hand side. So it says this is dx times the integral. So both, you can think of dx cancels on both sides. Okay, that's just the size of the volume. But here, the right-hand side is dx times the integral from minus infinity to infinity. The density function x minus delta at time t. This is the earlier density, times this is the jump distribution, phi of delta times d delta. What on earth does this mean? What on earth does this mean? So let's consider, say, how can the particle end up here? So originally you have how can the particle end up here at the new time instance? Yeah, this is a convolution, right? This is indeed a convolution, but we wish to justify this. So originally, at time t, you have the distribution f, right? f of x and t. This is the old distribution. And x minus delta, that means, hang on, x is here, x minus delta, say x minus delta is this. X minus delta is this. That means the particle experiences a jump of size delta. And that happens with probability, that happens with probability over here, phi of delta times d delta. So this is indeed the n, right? N times phi of delta times d delta. That's the right-hand side. And now you're just integrating over all possible values of delta. Okay, let's take a look at the footnote here. Einstein actually wrote f of x plus delta t in the integrand, which is incorrect. Why? The sign has been corrected for all subsequent equations. In the case considered by Einstein, however, the collisions are unbiased, so the sign makes no difference whatsoever. But let's think about why it should be minus instead of plus. Right, so for here, if delta is considered to be any real number. So if the original position is x minus delta, then it needs to travel exactly delta to be here, or x plus, or close to delta, in the sense of delta plus or minus dx. It does not matter here. Okay, so for a position at an earlier time instance t to travel into this new volume of interest, its position change needs to be delta. So that's why the original position is x minus delta, hence the minus sign. Right. So dx times f is the number of particles. Dx times f is the number of particles, and times phi delta d delta gives you dn. So now this integration just tells us the conservation of total number of particles. You should put dx inside here, and the right hand side is the dn, and you're just integrating all the dn's, and of course the number of particles don't change. That makes sense. So that's the physical argument. Okay, let's just walk through this one more time. Okay, this is very crucial here. Dx times the f of x minus delta dt, this is what? Well, that's the number of particles. That's the number of particles in this time interval, x minus delta and x minus delta minus dx plus dx. In this volume, with also length delta, with also length dx, has this many particles at the previous time instance, and they all travel with sized delta, and the number of particles that makes that move is this number here, is this product dx times f times phi of delta d delta, which is this assumption, follows from its assumption 1.2. And now you integrate over all possible values of the transition. Okay, so I hope we're clear here. If you were a cat, what color cat? I was wondering. I mean, I'm not a cat, but hi Leo. Yeah, I have two cats, one tabby, one gray. Okay, so let me catch up with chat. So chat has a lot of question here. So if we normalize nu, we get a distribution parameterized by t, stochastic process. Well, the stochastic process is x. The stochastic process is really just the trajectory of the Brownian particle. That's the stochastic process, not the number of particles, I would say. But if you say, I mean, of course, x is a random variable, right? And f is a deterministic function. F of x and t, of course, would be a stochastic process as well. But I think perhaps it's more intuitive just to think of the position as a random process or stochastic process. Yes, the number of particles jumping in and out, that was basically what we said. How many were at x minus delta and those who got shifted? Exactly. You phrased it better than I did. Here, just to add a note that includes in and out of the interval, when delta is positive, that talks about the particles moving out. Yes. Can you repeat one more time y minus delta instead of add? Cool. I'll do that. So delta is the displacement. Increase. You see, this is increase. Basically, that's why. The x-coordinate increased by amount of delta. So going towards the right means delta positive, and the left means delta is minus. Delta is negative. Okay, so here we're considering the number of particles after increasing its x-coordinates by delta is found in the control region, the region of interest. So that must mean the original position is x minus delta instead of plus. Is that clear, chat? Because delta up here is assumed to be increment. X coordinate of individual particle increased by amount delta. So if the coordinate increase by delta and land x to x plus dx, its original position must be between x minus delta and x minus delta plus dx. Okay, cool, we're good. And now another sleight of hand. Okay, since tau is very small, you can use a linear approximation, first order Taylor expansion in T. Okay, once again, we're assuming f is very smooth, obviously, when we do that kind of thing. Okay, classic physics. I'm not talking about classical Newtonian physics, but this is something physicists do all the time. Assuming it's smooth until things go wrong, okay, and then re-examine what happened. But right now, let's just assume this is smooth. Okay, assuming the density is smooth in tau, then what we're going to do next is to write the integrand, a part of the integrand, f of x minus delta, as a power series, another Taylor expansion. And this time, perhaps a little bit puzzling. Here we keep two terms. Why do we keep two terms? Because if you just keep one term, as we shall see, after integration, the first order term, okay, disappears. Okay, so here 1.6, the approximation, linear approximation in T is used on the left-hand side because this is T plus tau. This is substituted on the left-hand side. And f of x minus delta t, this is the second order Taylor expansion in big delta, is used on the right-hand side. Okay, let me actually do the calculations. Just do the calculations. So let me do the calculations of these steps. So 1.5 is Einstein paper. 1.5 is f of x of t plus tau dx equals dx times integral minus infinity to infinity f of x minus delta t times phi of delta d delta. Okay, so the left-hand side, we use the linear approximation in T, f of x t plus tau equals f of x t plus tau times the partial derivative df over dt. Okay, and on the right-hand side, we use a second order Taylor expansion. The reason for that will be apparent soon. F of x minus delta of t is a Taylor expansion. F of x minus t, Taylor expansion in the first variable, minus delta df over dx plus delta square over 2 factorial d square f over dx squared. Okay, and then substitute. Okay, let's do the substitution and see what happens. Substitution into 1.5. So on the left you have f of x and t dx plus tau df over dt dx. This is the left hand side. On the right you have dx times the integral minus infinity to infinity. Here the Taylor series. Assume you can integrate term by term. Once again, no justification whatsoever. Okay, just do the expansion. F of x and t, phi of tau, sorry, not phi of delta d delta. But notice the zeroth order term has nothing to do with tau, so it can be taken out of the integral here. We just put it this way. D delta. All right, so that's the first term. The second term is this. Okay. By the way, these partial derivatives are all evaluated at the base point. Here, let me just write it this way. Okay, df over dt is a shorthand for df over dt at x and t. Okay, same as the first term. This is just Taylor expansion. We all know that. And df over dx means the same, okay? It means the df over dx evaluated at x and t.
So these aren't dependent of delta. This way they can all be taken out. Okay, so here delta df dx, so this one can also be taken out of the integral. And then phi of delta d delta. That's the first order term. Let me just pull this out as well. And the third term would be plus, okay, integral minus infinity to infinity delta square over 2 factorial second partial derivative d square f over dx squared times phi of delta d delta. Okay, once again, this can be taken out of the integral. So what happens to each term on the right-hand side in particular? Well, the first order term, the zeroth order term, is just a normalization condition. The zeroth order term is just dx f of xt. These are just like moments, exactly. These are just moments of delta, exactly. You're completely right. Okay, and the second term is 0. Okay, here we're using the fact that the integral of phi of delta, this is normalization. This is 1. The first order moment vanishes because earlier we assumed the symmetry or evenness in phi. So delta times phi of delta is an odd function, and this of course vanishes. This is 0. Zeroth order moment is the first order moment is 0. So that's why you can't just keep the first order expansion. You have to go to one term further. Okay, and of course the higher order moments are ignored in, once again, typical physicist. Okay, minus infinity to infinity delta square. This is basically the second moment. This is the second moment. There's no reason that this thing will vanish, and in fact it doesn't. This is the second moment. Okay, so plus 0 minus 0 plus got d squared f over dx squared integral from minus infinity to infinity delta squared over 2 phi of delta d delta. Okay, so what ended up happening is you have a cancellation here. Dx times f of x and t also cancels. And now you can rearrange. Oh, I forgot to put dx here. Dx here, dx here. Okay, so dx on both sides cancel. So now you have both sides dx cancel, and we do a rearrangement and put tau on the right. Tau is a constant. It is a constant in the analysis. So df over dt equals d squared f over dx squared integral from minus infinity to infinity delta squared over 2 tau phi of so actually let's put it this way, 1 over tau, because I don't want to mix up things. Delta squared over 2 phi delta d delta. So now this is just a constant, and this is what we call d. So the PD is derived. Yeah, wow, there's a PD on the right now. That's exactly what happened. So let's continue. Okay, so this is just substitution. You have this law of total probability, aka the conservation of particles. This is basically a conservation law. And now you use the Taylor expansion on both sides, 1 in T, 1 in delta, and boom, heat equation or diffusion equation happens. Okay, let's keep going. So yeah, we can use this series under the integral because only small values of delta contribute to this equation. Okay, we're assuming higher order terms don't matter. Then we have this, right? Assuming term by term integration is valid, then we have this. Because you have symmetry, the second, fourth term, etc. term on the right hand side vanish. That is the first order moment third order moment, basically all the odd order moments, they all vanish. Okay, so which each one is very small compared to the previous. We obtain from this equation by considering into the consideration of normalization, and we just call this constant big D, and keeping only the first and the third term of the right hand side. Right. So F cancels. You only have time derivative on the left and the third term on the right, and boom, heat equation. This is already known as the differential equation of diffusion, and it can be seen as D is the diffusion coefficient. Okay, so classically, the diffusion equation, so Einstein did not discover this. Okay, so Einstein did not discover the diffusion equation on its own. Right? This was due to Fourier, actually. Right. Actually, you know what, guys? Let me just, for comparison with the derivation of diffusion equation by the Fourier argument. It's a nice application of vector calculus. No probability involved. By Fourier. Actually, Fourier initially developed the heat equation. Right? So, but Fourier developed the PDE in the context of heat transfer. But later, the same argument was employed by Fick, I believe. By Fick, in the context of diffusion. So Fourier did it for heat, and Fick did it for diffusion, and Einstein did it for random walk. So you see, these are, on the surface, macroscopically speaking, distinct phenomenon, but the underlying mechanism is the same. So consider a body in R3. A body of liquid, solvent, so to say. And this is our control volume. I say this is the control volume. We consider this is our region of interest. Say omega is an arbitrary region of interest. And now by the conservation of particles, so that is to say the rate of change, okay, the rate of change of omega, not omega, rate of change of the, so to say, the amount of particles. In omega can be expressed in two ways. First, let's denote rho, the density of the particle, rho of x and t. So here x is in fact a 3D coordinate, rho of x, y, and z. So let's write it as the integral of rho x as a vector, t, and then dv. So that's the number of over the integral over, this should be a triple integral, okay? Triple integral over omega. Let's write triple integral, not be lazy. So that's the number of particles, or not the number, but just the amount in terms of mole, okay? Amount, use the chemist unit, mole. In mole, okay? So that's the amount. So that's rho. Or you can write it C, perhaps. That's the chemist notation, right? Concentration, you use C. Let's use C. Moles per volume. Right? And the rate of change is just d over dt of that. Because we assume conservation of material, nothing is created or destroyed inside omega, the rate of change can only due to the flux across the boundary. Right. So let's write the flux integral. So this is, let's draw, this is the outward normal vector. outward normal vector n of the surface. And the flux q may not be in that direction. So q, the flux can be arbitrary. The direction q, this is a flux. Q of x and t, this is a vector. Right. Q is the flux. So basically that's you can think of the amount of particles that moves, Q is a vector, so it has a direction and has a magnitude. The magnitude is the number of particles per area that move across that area at time t. To think of a water tap, right? So if you think of a water tap, you can easily picture what this Q is. The faster the flow, the larger the Q, and of course Q carries the direction of the water flow. And because of, as I said, the normal vector may not align with the direction of Q, you need a dot product. Why do you need a dot product? Because only the normal component matters here. The tangential component will not cause leakage, will not cause the loss of gain of particles in that region. Only the normal component of Q will contribute to the gain or loss of particles inside that region. So therefore, here you need a double integral over the boundary of omega, and q of x and t, taking dot product with n, and then ds. ds is this little area. But here, because q n is outward, there should be a minus sign. There should be a minus sign. So this is just a conservation law. Minus sign is due to the choice of the outward normal vector. Okay. So this causes the loss. Q, as this diagram shown, it causes the loss of particles inside the region. So therefore, we could put a minus sign here. Okay. So now what we can do is we assume you can differentiate under the integral sign, assume regularity. The left-hand side becomes the triple integral over rho, so triple integral over omega, and then partial derivative dc over dt, dv. This is the left-hand side. Interchange the order of differentiation and integral. On the right-hand side, what we can do is to use a divergence theorem, or Gauss's formula. Gauss's divergence theorem on the right. This is a flux. By the Gauss's divergence theorem in vector calculus, this can be converted into a volume integral. Doing so is quite natural because on the left you have a volume integral and on the right you have a surface integral. They cannot be directly combined, right? So you can transform the other side to a volume integral, and that's exactly the divergence. The divergence of Q. Often we write it as the nabla dot with Q. Same as divergence of Q. Divergence, of course, this is with respect to x coordinate only. Okay, and then dv. So that's on the right. And now you can combine the two terms. This is, actually here on the right is omega. So for this control volume, we have the conservation law that reads, okay, dc over dt plus the divergence of the flux, dv equals 0. And essentially, we did the same derivation for the traffic flow PDE in 1D. In traffic flow PDE, the material is car. Here we're dealing with fluid particles here. So assuming continuity of integrand dc over dt plus the divergence, this is continuous. Assume this is continuous in any region, omega, okay? In any region, omega, then the integrand must vanish. Now, there's a theorem that justifies this. If a continuous function has zero integral over any arbitrary region, then it must be zero everywhere. So dc over dt plus the divergence of x, q equals 0. So that's just the conservation law. Right? So the conservation law has two forms, one in integral form, one in differential form. And the key of this derivation is the divergence theorem. Here we use this Gauss's divergence theorem from vector calculus. And now we need to introduce an extra assumption. So this is Fourier's law, or Fick's law. Fourier and Fick assume that Q has a relationship with C. Remember, C is a density field, or a scalar field. And Q is a vector field. So think about how intuitively how particles move. The idea is diffusion happens to level the distribution, to make the distribution as smooth as possible. So let's just say if at one position the density is high or the concentration is high, on the other point the concentration is low, the flow should go from high to low. And how can you describe this directionality from high to low for a scalar field? Of course, you use the gradient. And that's exactly, this is go from high concentration. Diffusion goes from high concentration to low concentration. So this direction should be the negative of gradient. Or there's no reason that it should be, but that's the postulate, concentration. So the Fourier and Fick assume that diffusion or heat transfer, Fourier assumed that the heat transfer goes from high temperature to low temperature. Fick assumed that diffusion happens from high concentration to low concentration. So basically, this law, or assumption really, this is a much more contingent assumption compared to the conservation law. Right. So Fick's law, or Fourier's law, says Q equals the negative of the gradient of C minus grad of C. Same thing. Okay. Actually, there should be a proportionality constant, which is big D. The diffusion coefficient, the diffusivity, or the in the context of heat transfer, it becomes the conductivity of the material. So basically, this is what Fourier and Fick assume. Okay, so D can be positionally dependent. D can be dependent on the. In fact, D in general is a tensor. D is the diffusion tensor. So D in general has 9 components and is assumed to be symmetric. Yes, earlier this is a continuity equation. Christian, you're completely right. Continuity equation. Well, we use the continuity equation in our traffic flow PDE as well, just in 1D. There we have the conservation of cars. Here we have the conservation of molecules. So D in general is symmetric. X, Y, X, Z, yeah. D, Y, X, D, Y, Y. So in general, you have a matrix or a tensor to describe the relationship between the flux and the density. Okay, so it's just a working assumption. Intuitive, but still subject to change if physical data says otherwise. So D is the diffusion tensor. So in isotropic diffusion, in the case of isotropic diffusion, then you just have one parameter in big D. D is just Okay, let me put the double bar here to emphasize this is a matrix. Okay, in the case of isotropic diffusion, it's just one scalar d times the identity matrix, 3 by 3 identity matrix, and this way q would actually follow the direction of the gradient. Okay, so that's now the complete description of the Fourier's law or the fixed law. Right, so this is an example of a constitutive relation. Constitutive relation or constitutive law. Essentially, it is an assumption about the material, the environment of diffusion. To assume isotropic diffusion, then we have this simple relation, where d is a scalar. D is just the diffusion coefficient. But once again, diffusion coefficient may still be non-constant. This can still happen, as in the case of stochastic process, as we will often see diffusion coefficient being non-constant. Right. So, but in the simplest case, we assume, as a first approximation, we assume diffusion coefficient is constant everywhere. In general, d still depends on x and t. Okay, but here, even just as a scalar, it can still depend on x and t. But you can, as a first approximation, you can assume d to be constant. So when d is a constant, actually, let me just substitute the q inside the continuity equation. This gives us the diffusion equation. Diffusion equation, just substitute the fixed law into the continuity equation, you get dc over dt, and then you get a minus sign on the right hand side, so you can shift it to the right hand side. This way you get the divergence of d times the gradient of c. So that's the diffusion equation in general. And in the case of isotropic equation, isotropic diffusion, and also homogeneous, in the case of isotropic and homogeneous, homogeneity of the material, homogeneous diffusion, then d is a constant, right? D is a constant and can be taken out. So it just reads dc over dt equals d, scalar d, times the divergence of the gradient. What is divergence of the gradient? We know from vector calculus, this is just a Laplacian. So this is just a Laplacian. You can write it as Laplace square c, the Laplacian. Or the Laplacian is defined as the gradient of the not gradient of the divergence, but divergence of the gradient. So that's the most common form of the heat equation, dc over dt, d times Laplace square of c. You see, this had nothing to do with stochastic process. This was already known when Einstein wrote his paper. And in 1D, this reduces to dc over dt equals d times d squared c over dx squared. Okay, so this is a completely deterministic model. There's no probabilistic assumption being introduced whatsoever. Okay, so Einstein developed the heat equation from a completely different angle, and the result was already something well known. Okay, so hopefully we're on the same page now. So the problem which corresponds to the problem of diffusion from a single point, neglecting the interaction between diffusing particle, is now completely determined mathematically, and the solution is a Gaussian. So the solution, so going from 1.11 to 1.12 is a lesson in PDE. Basically, you do it using the Fourier transform. Yeah, using the Fourier transform allows you to get this equation. The initial condition is a delta. The initial condition f of x and t, f of x and 0, the initial distribution is just delta of x, just a point mass concentrated at 0. And then going from, you can derive this equation, derive the solution using the Fourier transform method. Okay, so I mean, we're just going to accept this for now because that's already enough digression to the original derivation of the diffusion equation. We will do this in our perhaps in our PDE live stream or our live stream on the Black-Scholes equation. Okay, I think, yeah, I will probably do Black-Scholes earlier than heat equation proper, so we'll do it that. It's promised we'll do that here. I promise I'll do that here. So basically, you can just take my word for granted. Okay, 1.112 is the unique solution of 1.11 subject to initial condition of just a point mass at the origin. Okay, so this is already an awesome result. So now we can, basically what we have here, remember, what is this F? What did we just solve? F is a particle distribution, number of particles per unit volume. So basically the distribution of X, distribution of X. That is the, you see on the axis, how concentrated the particles are. You can think of this as a concentration, basically. The number of particles, n, per unit volume. And now you have a distribution, you can calculate its moment. Right? Now you can calculate with the help of this equation the displacement of lambda x in the direction of x-axis that a particle experiences on average, or more exactly, the square root of the arithmetic mean. Oh, by the way, this notation right here, angle bracket, is the direct notation in physics. This means expected value of big X squared in statistician's notation. Okay, and we will use the physics notation. Okay, because this is, after all, stochastic processes for physicists. We will follow this definition. Okay, I just want to be extra clear here. Okay, this stands for the average. This is the notation you will find in statistical mechanics textbook and in quantum mechanics. I know this drives statisticians crazy, but just try to accommodate to other culture. Okay, so well, of course, if you already know, this is a Gaussian, by the way. What is this Gaussian? It has zero mean. Let me write the general form of Gaussian. In statistics, we say x, random variable x, follows a normal distribution with mean mu and sigma square as its variance. It means its density, f of x, is 1 over square root of 2 pi sigma square times e to the minus x minus mu quantity square over 2 sigma square. We've been using this formula a lot in our mathematical statistics series. So here, basically, you see x minus mu squared is just x squared, and that means mean is constant 0, which makes sense. So on average, Brownian motion does not create a net displacement on average, right? Which would be crazy if it does, right? So yeah, so imagine, like, if on average Brownian motion create a net displacement, you pour your water like this, and at some point it becomes like this, it would be absurd, right? So on average, the macroscopic distribution of the particle don't change. However, there's incessant microscopic motion going on at all time. So the mean don't change. That's cool. And here we're essentially taking the square root of the second moment. Or basically this is a variance because the first moment is 0. And what is the second moment compared with the general Gaussian distribution? You see sigma square is 2dt. Sigma square is 2dt, and therefore here we have this lambda x. It's called the root mean square, right? In physics or in engineering. Root mean square, power, or something like that. Energy used a lot in electrical engineering. So basically you take the second moment in it and then take the square root. It is proportional to the square root of t. So basically the variance grows linearly in t. All right? So that's cool. And this is something actually we also observed in our PDE series. So there we go. Here I remarked that earlier in the PDE live that the second moment for the birth and death process, in a special case where you have perfect balance between the birth rate and the death rate, so on average there's no mean displacement. You see the symmetry between this and the Brownian motion, analogy between the Brownian motion. Yes, that's just the standard deviation, exactly. That's just the standard deviation. Here, in the birth and death process, I also remarked that sigma squared grows linearly because d sigma squared over dt is a constant. So in that case, the standard deviation grows linearly. And in the diagram here, so in the perfectly balanced case, the average don't change, and the spread grows approximately at a rate of a square root of t. So here we're doing very much the same thing. The solution, let me just write it down. So the solution with initial condition C, here I use C, okay, C of x and 0 to be delta of x, direct delta function. So this is the diagram. Initially it is completely concentrated at 0, and then as time evolves it becomes a Gaussian that spreads out linearly. The variance grows linearly. So you can think of, let me label the curves, not very symmetric, but hopefully this is understandable. T equals 0 is just a single delta at x equals 0. Okay, and this is t equals 1, and this is t equals 2. As time gets larger, the spread grows larger. So C of x and t, so this is 1 over square root of 2 pi, actually 4 pi, 4 pi dt, e to the minus x squared over 4 dt. Indeed, the standard deviation mean is always 0. This is a Gaussian, right? This is a Gaussian with mean 0. And standard deviation equals the square root of 2 dt. Standard deviation grows at a rate of a square root of t. And this is exactly also how random walk behaves. Right? As we explained in our stochastic video series, the defining characteristic of a random walk, discrete time random walk, is that the standard deviation grows at a rate of the square root of the time step. This is a complete analogy in the continuous time. All right, so now coming back, so this is the end of the excerpt of Einstein's paper. And then it says the temperature T, right? More physics. The temperature T, the viscosity of the surrounding fluid, viscosity, nu, can be measured with the care of suspension of particles of a fairly uniformly radius r may be prepared. With the care, a suspension of a fluid, suspension of a spherical particles of fairly uniform radius r may be prepared. Okay, great. The diffusion coefficient d is then available through the statistics of Brownian particle via equation 1.13. I'm not sure if it's here actually derived. Oh, yeah, the statistics. So basically, the idea is you're going to prepare all these particles, and you're going to calculate sample statistics, right? You track down individual trajectories, and then you measure the standard deviation. Right? Basically, that's what it means. The point is you can calculate the sample standard deviation, and then infer what d is. How do you describe the distribution from first principle? Good question. This requires a Fourier transform. Let me see in the appendix whether this is reviewed. Okay. Basically, this becomes a problem in PDE, pure PDE, okay, the Fourier transform. Is there a derivation there? Direct delta, generalized Fourier transform. No, not here. Unfortunately, not here. But basically, I apologize for skipping over this part of the derivation. It is not in the main text here, but basically, this is a classic result in PDE. You can derive the Gaussian distribution using the Fourier transform. Okay, I hope this is not too much of a disappointment, but we will, of course, cover the solution of the heat equation in either the PDE series, I think in both the PDE series as well as the Black-Scholes, explanation of Black-Scholes. I hope I can get to Fokker-Planck this week. We will do a little bit of a marathon of stochastic process in a stochastic process in physics this week, well, stochastic process for physics this week, and I wish to discuss option pricing and Black-Scholes next week. Okay, so over there, okay, so we will definitely derive this famous equation from first principle. Okay, I'm not gonna just hand wave over this one. This is such an important result. So you see how amazing Gaussian distribution just seemingly appears everywhere, right? How amazing Gaussian distribution. It's just like, I mean, I made two characterization. I made two videos, each on one characterization of Gaussian. One is rotational invariance. That was perhaps the first video that that made my channel a little bit more, helped my channel gain a little bit of attraction. So if you go to the mathematical statistics series, actually I'll do that myself. Okay, hang on, where's math statistics series and math with Ming? Go to the playlist section. Playlist, yeah. Hang on, where's the mathematical statistics live? No, not live stream, but just videos. Here, yeah, the physics of Gaussian distribution. This is a characterization of Gaussian through geometry, rotational invariance. A corollary for that is the t-distribution. T-distribution is obtained purely from the geometry of a sphere. And the second characterization is here. The origin of normal distribution is the Gauss's error law. Gauss's error law. So another way to derive normal distribution. And here we see the third one from diffusion, from a PDE. How amazing is that? Yeah. Just astonishing, in my opinion. Okay, and of course there's the central limit theorem, right? The central limit theorem perhaps is the most famous context where Gaussian distribution arise. But it doesn't have to be the only one. In fact, it's not. So pretty cool in my opinion. Anyway, so here, the diffusion coefficient. So Einstein actually developed, I believe, in his original paper, the equation for D, namely 1.1. Yeah, here it says, for a spherical Brownian particle of radius R using Stokes' theory. So this can be derived theoretically. So now you have a verifiable theory. You can measure T, R, and nu and calculate D this way, or you can calculate sample statistics of the Brownian particle. Right? You can measure standard deviation and then deduce D that way and compare the difference. This way you have a verifiable physical theory, even though the individual assumptions earlier are difficult to verify. For example, statistical independence. This is in general notoriously difficult to verify. So these working assumptions, independent trajectory and whatnot, these are very difficult to verify. But here we have a verifiable, something that is measurable. You can measure the standard deviation and deduce the diffusion coefficient from this relation. And then you can compare that with the theoretical formula from Stokes' drag law. And actually, because of the good agreement between this theory and the earlier formula 1.1, that cemented this explanation, cemented Einstein's explanation as the ultimate explanation of Brownian motion. So this one finally explained the Brownian motion. The Brownian motion was discovered in the earlier part of the 19th century. It remained unsolved until here. Okay. So, in this way, the Boltzmann's constant, or equivalently the Avogadro's number, can be determined. This program was undertaken in a series of a laborious experiment by these two fellows, resulting in a Nobel Prize for pairing in 1926. So the coupling of equation 1.1, that is the diffusion equation from Stokes' drag law, and the standard deviation in terms of the diffusion coefficient. The coupling of those two is one of the earliest examples of using fluctuations to quantify a physical parameter, as opposed to simply considering the average behavior. Because here, average behavior is not informative. Right? On average, Brownian motion has a displacement of 0. It's the fluctuation that quantifies d. Right? So imagine here, in the earlier theory of diffusion, d is this physical parameter that characterizes the relation between flux, right? Q is flux, and the density. It is actually a statistical phenomenon. It is the result of a standard. It is basically decided by the standard deviation. This is a second moment phenomenon, to put things a little bit vaguely, right? So d is fundamentally the proportionality constant in the second moment. The fluctuation of the physical system quantifies a physical parameter. Said in another way, it is the irreproducibility of the experiment that is reproducible. Because, the trajectory are stochastic, right? You can't reproduce that. But the statistics is reproducible. Right? So, Einstein's argument does not give a dynamical theory of Brownian motion. Right? So, for example, there's nothing said about this sort of collision. Right? Because even though that's the underlying physical picture, right, we did not describe the dynamics. So that is to say how the particle is influenced by the collision. So that's unexplained in this derivation. Okay. Here, it says, it only determines the nature of the motion and the value of the diffusion coefficient on the basis of some assumptions. Shmolochalski, this is perhaps a less underrated person. Shmolochalski is also a founder of modern theory of Brownian motion, even though Einstein got the bigger credit. But Shmolochalski's argument is equally, if not, I think, in my opinion, Shmolochalski gives an equally valid account. Independent of Einstein, attempted a dynamical theory and arrived at equation 1.1 with additional factor. This is interesting. I don't know where that comes from. 32/27 on the right-hand side. This is apparently explained in another section. Okay, cool. So this is by Shmolochalski. Equation 1.1, remember, that's just d in terms of temperature, viscosity, and radius. So Shmolochalski also got this result with an extra factor. Interesting. Shmolochalski also laid the foundation of a more extensive study of Brownian motion, including the possibility of various forces acting upon the particle. For example, what if the particle is subject to gravity buoyancy, electrical field, that kind of stuff. So yeah, Shmulchovsky also considered Brownian motion in a potential field. Langevin, Paul Langevin, French physicist. Shmulchovsky, I believe, he was Polish. Langevin was French. Langevin provided another derivation, so we'll see Langevin's derivation. Yeah, another unsung hero, definitely Shmulchovsky. Langevin is perhaps more well known because Langevin's equation is actually very famous in physics. Shmulchovsky, I don't know. Perhaps among physics folks, he's also a hero, but definitely not as famous as Einstein. So all these people, they laid the foundation of stochastic modeling of physics. Langevin provided another derivation of equation 1.1, interesting, which is, this will be derived later, which is the starting point of the work of Ornstein and Uhlenbeck. Ornstein and Uhlenbeck, Ornstein-Uhlenbeck process is something that we will definitely cover in the stochastic calculus series, because this is a very nice ODE that has an analytic solution. Okay, anyway, so this is what comes next. Section 1.2.2, section 1.2.3, and section 1.2.4. Einstein's work was of great importance in physics, for it showed in a visible and concrete way that atoms were real. Quoting from Einstein's autobiography, okay, the agreement of these considerations with experience together with Planck's determination of the true molecular size from the law of radiation for high temperature convinced the skeptics, who were quite numerous at the time, including Mach. Mach, I believe, was also a skeptic of Einstein's theory of relativity, if I recall correctly. Mach. So the Mach number is named after him. The ratio between the speed of a object moving in the fluid and the speed of sound in that fluid. Right. In our ballistic series, we've already seen the importance of Mach number. Mach number is a crucial factor in the drag coefficient. So anyway, Mach was a famous physicist at the time, but apparently he did not believe in atom. Just to give an idea how widespread that skepticism was at the time. The antipathy of those scholars towards atomic theory can indubitably be traced back to their positivistic philosophical attitude. Okay, well, so this is getting very philosophical. I believe Mach was a positivist. This is an interesting example of the fact that even scholars of audacious spirit and fine instinct can be obstructed in the interpretation of the facts by philosophical prejudices. Okay, very interesting remark. Okay, so Einstein's derivation is really not just fundamental when it comes to deriving the heat equation and explaining Brownian motion, but in fact it laid the foundation for the rest of the course. And here is what Professor Scott had to say. The relation between Einstein's derivation and the rest of the course is as follows. And this is actually following Gardner's organization, Gardner's handbook. Now, Einstein's work anticipated much of what was to come in the study of stochastic processes in physics. A few key steps will be highlighted with reference to the appearance later in the course notes. Quoting from Gardner's handbook, equation 1.5. Remember earlier we said, oh, this is the conservation of particles, right? 1.5. We spent a great deal of time on this. Right? And I also remarked this is basically the law of total probability in probability theory. And that's the Chapman-Kolmogorov equation. Basically, it's a definition of, you can think of this as a definition of conditional probability. Or a consequence, right? Not quite the definition of conditional probability, but a direct consequence of the definition of conditional probability. So this is actually very fundamental, not just for Brownian motion. So equation 1.5 generalizes to the CK equation, Chapman-Kolmogorov equation, that says the probability of the particle being at the point x at a time t plus tau is given by the sum of probabilities of all possible pushes delta x. Right? Remember the diagram here. So to locate, to arrive in this control volume x plus to arrive at this control volume x to x plus dx, the particle originally at x minus delta to x minus delta plus dx needs to be pushed by delta to get into this new position, right? And now you just consider all the possible sizes of push, and then you sum them over. The sum over the probability, or the sum over all the dn's, equivalently speaking. So that's the law of total probability, aka the Chapman-Kolmogorov's equation for Markov processes. Right. The law of total probability applied to Markov processes gives you the CK equation. Okay. This assumption is based on the independence of push, delta, of any previous history of motion. It is only necessary to know that the initial position of the particle at t and not at any previous time. This is the Markov postulate and the CK equation, of which equation 1.5 is a special form. It is the central dynamical equation of all Markov processes. So Markov process says only the information at time t matters, and if that's given, the history before t can be ignored. And this directly parallels the situation in ordinary differential equation. So in ordinary differential equation, x dot is f of t and x. Right. So in Newton's law, and pretty much all of the classical physics can be written in this form. Perhaps in a PDE variant. Well, for electrical dynamic field, you need a PDE variant. But basically, the idea is if you know the initial condition of a system, then the equation of motion, or the equation of time evolution, will give you the complete trajectory after. And under certain regularity condition on F, you have a theorem called existence and uniqueness theorem. The trajectory after t is uniquely determined. Let's call this t0, okay, not x of 0, the x of t0. The initial condition is completely sufficient to decide what happens after. So F is, in general, a time-dependent vector field. It's a vector field. And if you know the initial condition, which is a point in the vector field, and then you can trace out the integral curves uniquely, if f is sufficiently nice. So Markov process is basically a generalization of this. It says the future might be random, but if conditioned on the present, then it is independent of the past. You do not need information prior to t0. The future might be random, but its evolution, the probability law of the evolution. So in the Markov process, you generally don't have unique trajectory after time, but the probability law that governs the evolution is only a function of the present state. It has nothing to do with history. So that's why Markov process dominates physical modeling. Markov process dominates the stochastic modeling for physical process, not other kind of processes like martingales, etc. Right. So pretty much this entire book is about Markov process. And of course, this is still an assumption. It's not a law of physics. Okay, Markov process is an assumption, not a law of physics. And in nature, you do have a non-Markovian noise as well, which is a separate topic. But overwhelmingly speaking, macro process dominates physical stochastic modeling of physical process. Hopefully that's clear. Okay, so the Chapman-Kolmogorov equation, and macro process will be studied in detail in chapter 3. So macro processes is a generalization of ODEs and PDEs. Next up, Fokker-Planck equation, equation 1.11. This is the diffusion equation. It's a special case of the Fokker-Planck equation, which a large class of very interesting stochastic process in which the system has a continuous sample path. And I shall remark that even for discrete process, it's interesting to look at its so-called diffusion limit. Even for discrete time process, discrete state process, because they're generally harder to analyze than continuous ones. So treating the Fokker-Planck equation as a continuous limit. Now, just like how Brownian motion is a continuous limit of random walk, as explained in our stochastic video series, the Fokker-Planck equation can actually be applied to study a discrete process as well, as a continuous limit. So it's very useful. In this case, that means the pollen grain's position, if thought of as obeying a probabilistic law, given by solving the diffusion equation, which is derived, in which time t is continuous, not discrete, as assumed by Einstein, can be written as xt. So xt, this is a stochastic process. I know, once again, this drives statisticians crazy. How can you use a lowercase letter to describe a random process? Once again, this is physics. Okay, just try to get used to distinct culture here. There's no such bureaucratic rule as saying, okay, random variable must be big X, little x is the quote-unquote realization. There's no such thing. X can very much be random, even for lowercase letter. This is a random process. Xt is a continuous function of time, but a random function. See, this is a stochastic process, the position process. This leads us to consider the possibility of describing the dynamics of the system in some direct probabilistic way. Right? So earlier in the Fokker-Planck equation, we only described the law of the stochastic process and not the stochastic process itself. Right? So here, the diffusion equation is about the probability law, or the probability density function of the stochastic process, but here, earlier, this derivation. Now, this is an evolution of the law. But sometimes we also want a more direct approach. How can we model, say, the position as a random process itself? So this leads to the stochastic differential equation, or SDE. In physics, this is often called the Langevins equation. Okay, so we have a random or stochastic differential equation for the path. It's a differential equation for stochastic process. This procedure was initiated by Langevin with famous equation that leads to this day that bear his name. See the following section. We'll discuss this in detail at the end of chapter 6. So there's a relationship between Fokker-Planck and Langevin's equation, or SDE. Because after all, they describe the same phenomenon. There should be a relation among them, and of course there is a general relation between them. For macro processes, you can, under certain conditions, you can establish a one-to-one correspondence between Fokker-Planck equation and the SDE. So statisticians, financial mathematicians like to work with SDEs directly, whereas physicists are more used to working with the Fokker-Planck PDE. Once again, different culture that creates this barrier of communication sometimes. Okay, next up. The next bullet point called the Kramers-Moyle, and similar expansion are essentially the same, used by Einstein to go from 1.5 to 1.11. Remember earlier, so how do we get the PDE? Well, you first have the conservation law, the particle conservation, and then you apply a Taylor expansion. Here we only kept a few terms, and you can keep more terms, and those kind of expansions are called Cramer's Moyle. So that's the expansion in its full form, Cramer's Moyle, and similar expansion are essentially the same, the use by Einstein. You keep the more terms, keep more higher order terms. The use of this type of approximation, which effectively replaces a process whose sample paths need not to be continuous with one whose paths are continuous, has been a topic of discussion in the last decade. Its use and validity will be discussed in chapter 6 and 4. So once again, physical assumption, I was asked about what does physical rigor mean. Right? Various approximations are only appropriate in different scenarios. So, and differences can be quite subtle. Now, whether certain expansions are valid or not. Right? And lastly, you have the fluctuation-dissipation relation. This is a theorem in statistical physics, a fluctuation-dissipation relation. So 1.1 is, remember, this is 1.1, and 1.13 is this one. So this allows us to express the diffusion coefficient in two different ways. So this connects the dissipation in the system with the magnitude of fluctuation in the thermal equilibrium. So and the general fluctuation and dissipation relation has many manifestations, including what's mentioned earlier in the electrical circuits as well. I believe this is called the Johnson's noise. Earlier here, the next major development in the study of noise that comes in 1950s and 60s through the analysis of electrical circuit. I believe this is in Gardner's book. In Gardner's book, chapter 1, on Johnson's noise. In fact, let's see the Wikipedia page for Johnson's noise. Johnson's noise. Okay, so you have this relation, also has to do with stochastic fluctuation. Johnson-Nyquist noise is the voltage or current noise generated by thermal agitation of the charge barriers inside the electrical conductor. It is also explained by the fluctuation dissipation theorem. Okay, so this is an electrical analogy of the mechanical Brownian motion. History of the thermal noise, you see. This looks a lot like, this is once again the RMS voltage. See, this is a lot similar to the diffusion coefficient we've seen in the Brownian motion. Of course, here I'm not going to go into the detail because this requires more domain knowledge. But you can see this particular example in more detail in Gardner's book. This one. Handbooks of Stochastic Method, also in chapter 1. Okay, so I just wanted to mention that quickly. So yeah, coming back here, the fluctuation dissipation result is a lot more general than we just seen earlier. You can express D in two different ways. Okay, Shmulachowski. This is Shmulachowski's ideas. Let's see how this is how this is done. Okay, independently of Einstein, Shmulachowski developed a complementary model of Brownian motion. Actually, my video on Brownian motion, actually, even though I put an Einstein on the thumbnail, it is really due to Shmulachowski, I believe. Okay, because the reason I put Einstein on the thumbnail here. This is my video. No. We have the. Hang on a second. Where's my stochastic series? Yeah, courses here. Yeah, just go to courses. You'll find the stochastic series. So in the stochastic series, I put an Einstein on the thumbnail, even though the approach I used namely a discretization, is due to Smoluchowski. Okay, because Einstein is so well known for explaining the Brownian motion, and so I just decided to put Einstein. But really, the exact approach I've chosen for my presentation over there is due to Smoluchowski. His original derivation has more in common with Rayleigh's study of Brownian motion. Okay, interesting. I believe perhaps it's because the scientific communication back in the day were not very advanced, so probably this approach here, Smoluchowski's approach, is already attempted by many others. Okay, so once again, credit is not the focus here. Okay, even though we do honor the work of those pioneers. Here, see exercise 9 on page 149. Although the essence of this argument and its legacy to the modeling of stochastic process can be appreciated by considering a spatially discretized version of equation 1.5. So 1.5 earlier was the law of total probability, right? That's the Chapman-Kolmogorov. And now let's consider a discrete version. Perhaps it's actually easier to understood than an integral, because integral always make your head spin, right? Whereas discrete sums are mentally easier to process. Okay, so in the addition of this discretization of time, still we use the same assumption on tau. Remember, what is tau? Tau is a small time interval compared to the overall observable time interval, but it is large enough so that you can apply the independent increment assumption. Right. So discretization of time, t plus tau, t plus 2 tau, etc. Imagine the motion of a particle is likewise constrained to discrete position. Not only we have discrete time, we also have discrete position. So now, instead of a continuously valued path, the sample path can only take the values in the set of discrete values. Right. And basically you have a lattice on the x-axis. And the grid size is delta x. Eventually, of course, we'll let delta x tend to 0. So that's the discrete position assumption. To fully characterize the model, one assign a starting position, generally x equals 0 or t equals 0, at t equals 0 for convenience, and a transition probability between lattice points. Here, figure 1.3, schematic illustration of unbiased random walk. Here, unbiased random walk means it is equally likely to go left or right. That's the unbiased assumption. In general, you can assume unequal transition probability as well. It's just that the difference equation becomes harder to solve. Right. So this is actually a simpler version of Einstein's original paper, in my opinion, which is the reason I chose this in my video. You can easily connect the discrete picture and the continuous version. The particle at position x can move to neighboring position x plus delta x and x minus delta x with equal probability during each time step. This is exactly random walk. At each time step, you either go from left to right. Okay, and now what do we want? Well, you can go two ways. You can write the stochastic process itself as a sum of random variables. You can certainly do that, and you can derive the difference equation, not differential equation anymore, difference equation satisfied by the probability mass function of the process. So let's see how that's done. Okay, Smoluchowski's model of Brownian motion assumes that a particle can move only one step to the right or to the left. Remember, what Einstein did was similar but less restrictive, right? Einstein assumed that in the time interval tau, delta tends to be small. Earlier here. So Einstein assumed that for very small values of delta, this is a continuous displacement. Phi is only different. Phi is the distribution of the jump. Jump distribution is only different from 0 for very small values of delta. That means with overwhelming probability, the jump size is going to be very small. But here in Shmuel-Chomsky, the only two possibilities are to the left and to the right of a small jump, delta x. So this is even more restrictive. But it turns out that this distribution doesn't matter. The exact distribution of the jump over a small interval tau doesn't really matter. Okay. Well, once again, because of the central limit theorem. The central limit theorem is basically allows you to ignore the details of the jump distribution and just be concerned about the sum. So anyway, here the position. Oh, okay. Here, yeah, it says Shmuel-Chomsky assumed the particle can only go one step to the left or to the right with equal probability. This type of process is called an unbiased random walk, an example of a more general case of one-step process. Right. So in our explanation of the birth and death process in our PDE lives, we also made the one-step transition assumption. The population either increased by 1 unit or decreased by 1 unit, one at a time. Mathematically, the conditional probability density, P of x and t, of the unbiased random walk obeys the difference equation. So consider, so on the left-hand side, this is the probability, oh, by the way, this is equals what? This is the probability of big X of t equals x. So this is it's now a probability instead of probability density, actually. But if you want to talk about density, you can say density with respect to delta x, I guess. Okay, but you can just think of it as a probability. There's no harm in that because everything now is discrete. Time is discrete, spatial coordinates is discrete. So this is the probability of big X equals big X of t plus tau. So this is what happens at next time instance. At next time instance, t equals time equals t plus tau. Say the position is at a point x, at a coordinate x. This is the new position. Well, if that's the new position, how can the earlier position be? What can the earlier position be? Because you have one-step transition, the earlier position only have two possibilities. It's just x minus delta x and x plus delta x, equally likely. So just 1/2 times the probability of being on the left earlier, and plus 1/2 times the probability of being on the right earlier. That's the law of total probability. You're summing up all the possibilities. And this is much easier than the integral, right? In the integral form, delta can be a continuous variable. So you can theoretically go from minus infinity to infinity. So instead of summing two probabilities discretely, you perform an integral. It's the same idea. Right? So here is just a very simple law of total probability, or the CK equation for Shmuel-Chomsky setup. And of course, at time t equals 0, you know the exact position. So it's a delta function. But here, instead of a direct delta, you use a Kronecker delta. It's a discrete delta. Okay. The two terms on the right-hand side of the equation represent the two ways in which a particle can move into position x during the time interval t to t plus t. How come everyone just keep retracting their message? I still didn't have time to read them. Like it's okay. But anyway, guys, thank you for the interaction in chat. This is a YouTube channel after all. Engagement matters. I'm sorry if I don't always respond to chat messages in a prompt way, because sometimes I just wanted to finish my train of thought. Okay, hopefully people don't get mad. Okay, sorry. So equation 1.14 can be solved explicitly. This can be solved explicitly using transform method. Now that's an exercise. You can solve this, um, but you can also what would be the prerequisite for this? Well, I explained in the beginning. The prerequisite for this is basic probability, non-measure theoretic. Okay, you need to know how to calculate mean and variance for discrete and continuous distribution. That's pretty much the probability prerequisite, and also differential equations. Ideally speaking, background in differential equations for ODEs and PDEs, basic solution method for ODEs and PDEs would be awesome. But if you don't know PDE, ODE itself is okay. ODE itself is okay because you only need a certain form of PDE, namely the heat equation, or more generally, second order parabolic PDE, and which can be learned along the way. But the minimum prerequisite is actually, guys, you know what? I'll give you the official prerequisite for the university, given by the university. University of Waterloo Applied Math courses, undergraduate. So this is a course at advanced undergraduate / beginning graduate level, like master level. Okay, so here these are all the applied math courses. Pretty cool courses. Some of them I didn't have access to when I was in the university. For example, 449 neural network, this was new. This is new, I believe. And scientific machine learning, this is very cool stuff, which I didn't have access to, but that's fine. Yeah. This one is 4777, Introduction to Applied Stochastic Process. Prerequisites. Okay, actually, let me go side by side. This is official prerequisite. Okay, this is just not me giving my own opinion. So, brief description. Here. Actually, here they actually do some more. So this is actually more balanced, I suppose. Probability basics and Brownian motion. So we're doing part 2 basically, and part 3 covers the engineering topic like Kalman filter. So yeah, we'll rotate between stochastic process for physics, for finance, and for engineering to accommodate different audience needs. But basically, this is a prerequisite. Coming back to prerequisite, AMS 250, 251, and 350 are all ODEs. So these are anti-requirement. Okay, if you take one, you cannot take the other. 251 is more advanced. 350 is a combination of ODE and PDE. But still, overall, 350 is mostly ODE. See, 350 is called differential equation of business and economics. Mostly, it is just ODE. There's a final 2 chapters on PDE and stochastic. Okay, so 250 is most students of applied math took because it's offered more. Introduction to differential equation. This is the first course on ODE. 251 is more advanced. But these are anti-requirement. If you take one, you cannot take the other 2. Actually, these are all ODEs. These are all ODEs. Stats 230 and 240. That's first course on probability. Exactly that I just said. So you need to know how to calculate mean and variance, just moments for continuous and discrete distribution. And nothing more advanced than that. You do not need, say, mathematical statistics. You need ODE and mathematical statistics. You need ODE and basic probability. No course on PDE is assumed. So, for example, 350. Wait a second, they don't offer it in fall? PDE, they don't. Okay, anyway, it doesn't matter. So yeah, 353, this is PDE. First course on PDE. I took this one. I quite like PDE, so I took PDE 2 as well, if I remember correctly. So basically that's it. Okay, that's the prerequisite. Not a whole lot. ODE plus basic probability. No measure theory, no real analysis, no PDE is assumed. Okay, so there's that. Yeah, so perhaps that satisfies. I'll say something about the prerequisite in the description because it seems like a popular question. Okay. As for bronze, you deliver gold law. Okay, no worries. I'm familiar with ODE, but not probability distribution. So, let me just say probability distribution. Let me give you the more specific prerequisites. Okay. We've been using the textbook by Evans and Rosenthal for mathematical statistics. I didn't cover the basic probability part. U of T. Evans and Rosenthal. Actually, you know what? I would use the Michael Evans, yeah, probability book. This one. So you see, for example, here, chapter 1 to 4. Even 1 to 3 is enough, I believe. Yeah, 1 to 3, all you need is how to calculate expectation. For example, you do not need things like central limit theorem, even though knowing that is helpful for this course. You do not need central limit theorem for that. So going from, just look at the book here, single PDF file. Yeah, I use this text for mathematical statistics, which is the second half of the book, for our mathematical statistics live stream. Last week we didn't have a mathematical statistics live stream because I did information geometry. That's enough statistics for me this week. That last week, so I skipped that. Okay, but you see, this is very much a first introduction to probability, and it's completely sufficient for what we're doing here. Okay, you do not need measure theory or advanced real analysis or any real analysis at all for today's live or what comes next in Professor Scott's note. Yeah, get yourself familiarized with common distribution. For example, here geometric distribution, binomial distribution, normal distribution. This will be very important actually. Poisson distribution also quite important for stochastic process because there is such thing called Poisson process, and especially normal distribution. Okay, so yeah, that's the background needed. Okay, so coming back to our main topic. Cool. So here, in many applications where X represents physical space, discretization is unnatural. Right? In problems where actually, you know what, guys? Let's convert this to PDE, shall we? Because let's convert this to PDE real quick. Okay. So I think everyone understands equation 1.14. This is actually much easier than the continuous law of total probability, 1.5. And by the way, when I'm doing the live, because it's much more helpful if you're also reading the same notes as I am, because this way you don't have to subject to me controlling which section of the PDF, not PDE, but PDF I'm looking at. Okay, so yeah, this is 1.5. A discrete version would be 1.14. So let's go from 1.14 to PDE, shall we? I think that's a helpful exercise to see why this is essentially the same argument given by Einstein. But it's now perhaps much easier to follow due to the discrete nature. The human brain seems to process discrete sums more easily than integrals. Yeah, discrete versus continuous, exactly. This is a discrete version. So this is by Smoluchowski. How do you spell Smoluchowski? Smoluchowski. Hang on. Yeah, Smoluchowski. Adrian Smoluchowski, I believe that's his full name. Hang on. So somebody said I was watching your video. Someone in chat says. Okay. Anyway, so it doesn't matter. It's a separate topic. My bad. I saw somebody was messaging me on my Discord server about book I'm using. It's in the stream link, and not in the stream description. So that's the Smoluchowski difference equation. This is difference equation. So we wanted to see the limit of this difference equation when delta x and tau goes to 0. So that's the diagram. X minus delta x and x plus delta x. Two possibilities. Okay. So let's first recall the discrete second derivative, finite difference approximation of derivative. Recall something. Finite difference approximation of derivative in Calc 1. So imagine you have a function f of x. Just single variable function, okay? This is f of x. And here you have x and h, x plus h. The derivative, of course, is the limit of the secant slope. Right, so this is f prime of x. F prime of x is the limit Yes, some of the distributions were indeed taking limits from passing limit from binomial distribution or binomial induced or derived distributions. Exactly. There are many analogies for such things. The normal distribution can be seen as a binomial, as a limit of binomial distribution. The exponential distribution can be seen as a limit, the continuous limit of a geometric distribution. The Poisson distribution can also be seen as a limit of a binomial distribution, but just a different kind of limit. So there's a lot of analogy between discrete and continuous distributions. Indeed, great point. F prime of x is f of x plus h minus f of x over h. So this is f prime. This is the definition of the derivative. So you can approximate f prime of x by a finite difference. You can approximate it in different ways. You can use a forward approximation, say f of x plus h minus f of x over h, exactly like in the definition. Or you can approximate it by a backward difference as well. So this is x, f of x minus f of x minus h over h. So there you go. This is finite difference approximation, FD approximation. Now, of course, this sort of approximation are fundamental for finite difference methods or finite difference schemes in numerical PDEs. Finite difference approximations. This is perhaps the the most natural way to solve PDE numerically. You use a discrete approximation of the derivative. This is forward approximation, and then you have a backward approximation. Right? So, but what about the second derivative then? The second derivative, of course, is just the derivative of the first derivative. So basically, you want to do the approximation. The approximate second derivative is the change in f prime over h. Right? Changing f prime of x, changing f prime of x over h. That's the ratio, the derivative of f prime. So what we're going to do is that we're going to use a forward approximation and a backward approximation for f prime to calculate the change. So here in the diagram we have x minus h as well. So imagine you calculated the slope of another secant, and then you just compare the, actually 2h. I think it should be 2h, huh? Am I missing something? It should be 2h or h. Huh. Okay, so let's use a forward approximation, which is f of x plus h minus f of x. This is a forward approximation over h. I think it just should be h. And then minus the backward approximation, f of x minus f of x minus h, quantity over h over h. And this just simplifies to f of x plus h minus 2f of x plus f of x plus h, minus h, over h squared. But I don't know it should be 2h or h. Let me check. Okay, let me just check using Taylor expansion. Let me just use Taylor expansion. Here's a quick check for this approximation. So f of x plus h by Taylor approximation should be f of x plus f prime of x times h plus half f double prime of x times h squared. Okay, f of x plus h minus h is f of x minus f prime of x times h plus half of f double prime of x times h squared. Okay, plus garbage. Okay, higher order term, little o of h squared plus little o of h squared. Okay, so let's take the limit. The limit as h tends to 0 of this ratio should be what? So when you add these two terms, the first order derivative term cancels. Yeah, and then you add the 2f of x together, so you cancel out with the 2f of x, so you just get, yeah, so this is indeed, see, the upstairs, the numerator is just f double prime of x times h squared plus higher order terms over h squared. This is just f prime of x. So indeed this is correct, right? So this is the FD approximation of second order derivative. In our PDE series, eventually we will discuss numerical PDE. So this sort of derivation will be quite common. To use this to derive the order of a numerical scheme, something like that. So this is basically the FD approximation of second derivative. Keep that in mind. Why do I mention this? Well, let's see the difference equation given by Smoluchowski and find out. So you see here we have x plus h and x minus h. Can we fill this up? Okay. On the right hand side. And what do we have here? X minus delta x and x plus delta x. Does that remind us of something? Let's see. Okay, so this is a Smoluchowski difference equation. Right here. And now we do what? Notice the similarity between the right-hand side of this thing and this thing. So we're going to do a manipulation. P of x, t plus tau. We wanted to leave some space here. You get 1/2 of P of x minus delta x and t minus 2p of x t and plus p of x plus delta x and t. So on the right hand side, we subtract by p of x and t. So we do the same on the left, minus p of x and t. So compare with this numerical approximation or finite difference approximation of a second derivative. Let's divide the right hand side by, well, delta x squared. Divide this by delta x squared and multiply by delta x squared. So things are balanced. Okay, what's going on the left? On the left, x is unchanged, but t goes from t to t plus tau. So why don't we divide that by tau? And to do so, we also divide by tau on the right. Yeah, so I believe I did this derivation in my video on the Brownian motion. I did this derivation, and there's a guy asked me in chat, not in chat, but in the comment. That's not a live stream. Asked me in a comment, how on earth did you think about this, right? If you've never seen this, you will never do it. Like, he seemed rather frustrated. But let me just go to the chat. Let me see this exact comment. Quite interesting. So yeah, because I just go from this step to this step without much explanation. My bad. I should probably mention this comes from the approximation of the second derivative, which I replied in comment. So here, go to my video on Brownian motion, which is my second most recent video. So yeah, there we go. We have the this is my second last video here. Yeah, I derived the difference equation basically the same as Smoluchowski's approach. Law of total probability, a review. Here, yeah, I just said, okay, rearrange and do this. Divided by delta x squared, multiply by delta x squared, and then divide by delta t on both sides. And there was a comment down here that seemed to be rather confused and frustrated. Why do I do this? I wanted to just make the text a little bit bigger. I don't know if it's still here or if that person deleted the comment. Because there should be a timestamp in there. See feature comment. What? I want all. I don't know. Maybe that person deleted the comment. But basically, yeah, I apologize if that step in the video is unnatural. But basically, this is how you get the motivation. You notice on the right there is x minus delta and x plus delta, and recall the approximation for second order derivative using finite difference approximation, and then you create this term here. So on the right, as delta x tends to 0, okay, as delta x tends to 0, this right-hand side, aside from this factor, this tends to the partial derivative. So t is constant here. All the t are unchanged, so therefore this is the partial derivative d squared p over dx squared as delta x tends to 0. And on the left, this is clearly as tau tends to 0, as tau tends to 0, the left-hand side becomes dp over d tau. Yeah, it's good to see some stochastic analysis here. Indeed, absolutely. I'm doing this to kind of reboot the stochastic stuff. What about this thing? The question is, what about this thing, right? What is delta x squared over 2 tau? This is unclear. The ratio is unclear because you have a 0 divided by 0 situation. Delta x tends to 0 and tau tends to 0 does not automatically give a limit to this factor. So we impose a condition. We impose a condition that this tends to a constant. Otherwise, we would not get a PDE. If the top goes faster than the bottom, then this would just be 0. So in that case, dp over d tau is 0, so p doesn't change over time. That's not what we want. Or you can have the top delta x squared grows slower than the denominator tau, in which case you'll get an infinity. So if tau goes faster than delta x squared tends to 0, then this factor tends to infinity. Then dp over d tau is infinity, which makes no sense. That means the rate of change of the distribution is infinite. So the only way to give us a PDE is to assume delta x and tau are not independent. Right? They tend to 0 in a coordinated manner. Assume tends to a constant d. So basically delta x squared, okay, is delta x squared. So basically you want the limit as delta x tends to 0. And delta you want, and delta, not delta t, but tau tends to 0, 2 tau. You want them to behave in a coordinated way. Like the two infinitesimals behave in a coordinated way so that it tends to a constant. So basically delta x is square root of 2d tau. And guess what? This is the Einstein's relation. It's this thing, but for a small time. So this has massive consequences later. If you guys have been following the stochastic series, this has massive consequences later because delta x, the size of change, here in the assumption, we assume that the process can only change delta x at a time during a small time interval tau. This is t plus delta tau. It can only go up or down. Those are the two possibilities. So overall, if you say let delta x tends to 0, delta tau tends to 0, and in a coordinated way, that is delta x is the square root of 2d tau, then you will get this infinite zigzag motion because delta t over tau is now, well, square root of 2d tau over tau, which is the square root of 2d over the square root of tau. And this, as tau tends to 0 plus, is infinity. So therefore, the slope of the trajectory blows up. And therefore, it is infinitely rough. The sample trajectories are all extremely rough. It is nowhere differentiable with probability 1. And that's actually the reason why Brownian motion needs a new calculus. Not because of randomness, okay, but because of the rough trajectory. And there's actually a new theory going on. It developed in just the last few decades, recent decade, I believe in the 90s, called the rough path theory. Guys, has anyone heard of this? I was actually given a request to do rough path theory, which is way beyond my current expertise, but perhaps we'll attempt so in a later stream. Just to raise awareness of this, it's called a rough path analysis or rough path theory. Yeah, theory was introduced in the 90s. It's a very new theory. So basically, it's all about studying how do regular calculus break down if you have rough path. Yes, rough path theory. So basically, Brownian motion is perhaps the first motivating example for rough path theory. The rough paths don't have to be stochastic processes. They don't have to be. They can be deterministic functions that are just highly rough, right? Highly rough, basically. That's we were interested in how do regular calculus break down. Remember, for Brownian motion, you need stochastic calculus. And in fact, infinitely. What's different about it? What do you mean by different? Right? I'm just saying that Brownian motion is perhaps the first non-trivial motivating example for rough path theory. No, that has nothing to do with Feynman path integral. Okay, so if you guys have been following the stochastic series, the idea is here. There is this video called Why Brownian Motion Needs a New Calculus, dw squared equals dt. The reason for that is because of the roughness. Not because Brownian motion is quote-unquote random. It has nothing to do with that. It actually has to do with the roughness. And the roughness here is given by this equation. This is a roughness of the Brownian motion. And this gives us, this compels the need of a new calculus. Basically, need a new calculus, meaning, for example, the Newton-Leibniz formula fails, the chain rule fails, the product rule fails. New calculus needed. It's because of this relation. You see, this relation is needed so that you get a PDE at all. You get a non-trivial PDE at all. Okay. In the Brownian motion video, here, I introduced this scaling law by a discrete analogy using the random walk. So basically, this allows us to get the Brownian motion, to construct the Brownian motion as a limit of random walk. Is there a trivial example of a rough path when it is not stochastic? Excellent question. There is. Actually, I gave one. In this video. I gave it in a video here. It's called where's the video? Is dx squared truly negligible?
When the change in sales dq is small, however, its square dq squared is very...
Come on, please. Yeah. So this is a non-trivial example, but it's deterministic. I'm not using the Weierstrass function because the cosine is difficult to manipulate. We simply need, this is a counterexample and it's completely deterministic. So it's called the Tarski-Landsberg curve. Why don't we play this video here?
On any point on the graph, it looks exactly as rough. Continuous but nowhere differentiable functions turn out to be fundamental
in stochastic calculus. The sample paths of Brownian motion turn out to be nowhere differentiable with probability 1. The classic calculus invented by Newton and Leibniz fails completely for stochastic processes driven by Brownian motion. And in case you don't know, we have a series on stochastic calculus, and you are very welcome to check it out. But in this video, we will give a completely deterministic counterexample known as Takagi-Landsberg curves, and we shall show that for some of its members, its higher order differentials cannot be ignored, just like in the Brownian motion. And here's the idea of the construction of the Takagi-Landsberg curve. We start with a triangle wave function. The value of the function is defined as the distance from x to its nearest integer. And now we're just going to make higher and higher frequencies of the triangle wave, with its frequency doubled at each time. So if we call the original triangle wave f of x, this is f of 2x, that is double the frequency. Doubling the frequency again, we get f of 4x. Doubling the frequency again, we get f of 8x, and so on. And now we have the formula for the TL curves. TA of x is defined as the infinite sum of a to the n times phi of 2 to the n times x, where n goes from 0 to infinity. Phi of x is the triangle wave. Yes, this is made in PowerPoint. The idea is we can make higher and higher frequencies of the triangle wave and add them together so that the real line is filled with non-smooth points. And let's see what the sum looks like in Desmos. It's highly interesting. In Desmos, we're only adding the first 10 terms in the infinite series, and this is what happens when the parameter a runs from 0 to 1. Amazing, isn't it? It's like baking a cake. And now let's investigate the sum of the second order differentials. Denote f of x as the Takagi-Landsberg curve with the parameter. That's the counterexample. You set the parameter a to be 1 over square root 2. Okay, and through some shenanigan, you can show that dx squared, or actually the sum of dx squared, is non-trivial. The sum of dx squared is at least 1/4 for all n. So it doesn't matter how finely you partition the x-axis, the second order terms will have a non-trivial contribution in the integration. Right? In the whole point of the video is dx squared equals 0. That's interpreted in this way. In regular calculus, the dx squared summation is negligible as delta x tends to 0 because the function is smooth. And when function is rough, like this, like Brownian motion, or just it has nothing to do with randomness, as that's the whole point. If it is rough, then it is possible for delta x squared to have a non-trivial contribution, in the integral. Okay, yes, this is indeed a fractal. Indeed, it's a fractal. Brownian motion is also a fractal. Brownian motion is a fractal. This is a fractal. The Weierstrass function, non-differentiable, nowhere differentiable function, the Weierstrass function is a fractal as well. These are all fractals. Okay, so I hope this cleared up the notion that stochastic calculus is only needed because of stochasticness. Okay, no, stochastic calculus is needed because of not because of randomness, but because of the roughness of the Brownian motion. If your stochastic process, say, is a smooth curve, then ordinary calculus works just fine. The sample path of a stochastic process is smooth enough, then go ahead, use Newton and Leibniz. It's because Brownian motion needs this scaling law, delta x and tau, in this manner. Because it needs this scaling law, so you need a new calculus. This is perhaps, I don't know, a confusion among beginners. The stochastic calculus is needed because of quote-unquote randomness. No, it's actually not. It's because of Brownian motion is very rough. That's why. So rough path theory is you can treat it as a field of stochastic analysis, but also it also works when for deterministic function that are very rough as well. It's just that in practice, such trajectories often arise as sample paths of stochastic processes. Okay, you got this rough trajectories from stochastic process. So rough path has a lot to do with stochastic, but it has nothing to do with stochastic per se. You can have a very rough deterministic function. Okay, do we have some notes here on the internet? Notes? Lecture notes on rough path. So for example, this is on archive. Application to machine learning. This is very advanced stuff. You need strong background in real analysis to understand what is going on. So do we have, for example, this is perhaps more application oriented, huh? Is there a, for example, let's start with the fundamental definition. Differential equation, some Lie bracket stuff. Tensor space, what is going on? Okay. Yeah, p-variation. Because what we seen earlier for Brownian motion is that it's quadratic variation. Basically, 2 variation is non-trivial. Right? Delta x squared is proportional to t. Delta x squared is proportional to tau, aka delta t. And of course, in regular calculus, you cannot ignore dt. So delta x squared cannot be ignored. Right, so we're going to generalize this notion for p-variation. And you see, this is completely deterministic. This has nothing to do with x being a stochastic process whatsoever. Okay. All you need is Arnold-style love for intuition. I mean, Arnold is tough love. I mean, just a side tangent that basically, Arnold is considered idiosyncratic even by Russian standard. Okay, Arnold's ODE is very hard, but still readable. Arnold's PDE is completely incomprehensible to me. Okay, I have not tried his mathematical method of classical mechanics in detail. I probably should, because I'm very interested in the subject. But basically, Russian, I mean, perhaps that's even a generalization. I'm saying Russian style math. In Russian style math, Arnold is still, it feels like he jumps between too many ideas for dummies like me. So anyway, what I'm saying is rough path has nothing to do with stochastics. Okay, this is too much of a digression. And there's this new field, relatively new field, called rough path theory. Okay, and of course, its origin traced back to Brownian motion, and perhaps you can argue trace back to the Weierstrass non-differentiable function. Basically, it's about how calculus breakdown, how much calculus can be salvaged or need to be modified when the rough path, or when the path becomes rough. Okay, Newton-Leibniz formula, the chain rule, all those good stuff only works for smooth path, differentiable path. Okay. Anyway, here, yeah, we just did that, right? Furthermore, in a certain limit, the Smolov-Trotsky model reduces to Einstein's diffusion equation, which we just did. Okay, so hopefully this is can give us more intuition of what is going on with Brownian motion and why stochastic calculus is needed, and not because of randomness, but because of rough path. Okay. Anyway, in many applications, perhaps, I don't know, like I started today at 6:30, so it's near 4 hours, huh? Near 4 hours. So perhaps I will just stop here. I'll finish here, and tomorrow. Actually, tomorrow there will be measure series. So on Wednesday we'll start with Langevin. Okay, on Wednesday we'll start with Langevin. So we'll stop here. In many applications where X represents physical space, discretization is unnatural. Here, yeah, we've already seen that. What is in that? Yeah, it's unnatural. In problems where state space is inherently discrete, such as molecule numbers or animal populations, Smoluchowski's methodology is particularly convenient. Right? Indeed, like in the birth and death process. It is not difficult to imagine whole classes of more complicated processes that can be constructed along similar lines by allowing, for example, multiple steps, biased transition rate. Yeah. Some of them will show up in the exercises. State-dependent transition rate. Right? Here we have uniform or homogeneous transition rate for all x. So let's suppose starting from a different x, the transition probability may change. Yeah, this can also happen. So these are generalization of Smoluchowski's model. And you can have multidimensional lattice, right? Multidimensional Brownian motion. Say 2D, you have 4 possibilities. This is also possible. These general models will be explored in more details in section 3.3. Okay, relation between Smoluchowski's formulation and the rest of the course. Master's equation. Master's equation. So the whole point of Smoluchowski's difference equation is that it simplifies the CK equation. Right? I said earlier that 1.14 this is a law of total probability, although a simplified version. And 1.5 in Einstein's derivation, this is also Chapman-Kolmogorov. So in general, Chapman-Kolmogorov look like this. In general, Chapman-Kolmogorov is an integral equation, a nonlinear one, which makes things very difficult to handle. So in certain situations, let's say if you assume only small jumps, then CK equation can be simplified to something like this. And that's called the master's equation. Okay, so here in the book it says the master equation, Smoluchowski's conceptual framework is ideal for many physical applications. Many physical systems with approximately chosen coarse graining of the observation timescale. Yeah, so the coarse graining timescale is exactly what we referred earlier as tau being not too small and not too large. There's a special term in statistical physics, or just physics in general, for this assumption. It's called coarse graining. It is small in a sense and is also large in a sense. It's a very delicate modeling choice. Okay. So coarse graining of the observation timescale can be represented by a Markov process. The main numerical dynamical equation for a Markov process is the CK equation. Under the same coarse graining of the observation timescale that permits the physical process to be described as Markovian. The CK equation reduces to more simple master equation. So remember we had that diagram earlier. CK equation can reduce to master equation in a certain situation. Basically assuming small jumps. Here, let's go to chapter 5. Yeah, so this is a logical route we will follow. Chapman-Kolmogorov equation governs all Markov processes. So in general, this is an integral equation and is nonlinear because of f times f. That's a nonlinearity. So this is very difficult to solve. Okay, and under certain condition, so this is so-called microscopic series. It means for short time period, only small jump is possible. Small transition is possible. Then you get the so-called master's equation. Very important for physics. Okay, so and then it can be reduced further to Fokker-Planck equation. In that case, you would assume that the density is quote-unquote a slow varying function of y. So this way you can expand P as a Taylor series, just like Einstein did, and ignore higher moments. So this way you get a second order PD This is a Fokker-Planck equation, which is chapter 6. Okay. So coming back to Brownian motion. Okay, so this is the generalization of Shmolechowski's approach. It becomes a master's equation. Can we solve them straight? Very difficult. Under restrictive circumstances, you can solve master equation exactly. We give one such example in the PDE live. For the birth and death process, a master equation can be solved exactly using a trick called generating function, but this is very rare. In general, master equation is still very difficult to solve, even though it is simpler than CK. Okay, CK is solvable for discrete time, finite state Markov chain. So this is called discrete time Markov chain. So CK equation can be solved exactly in a discrete time finite state Markov chain. It's just a matrix power. So that's a simple situation. In general, CK equation is impossible to solve. So you have to make approximation assumption or just more restrictive assumptions. So anyway, the random walk is an example of a master equation with discrete state, equation 1.14. This one right here, the difference equation. This is 1.14. This is an example of a master equation. Okay. Here, the random walk, so in practice, the physics of the process are captured by the transition probabilities among lattice site. Then the master equation is used to predict how the state evolves in time. The master equation is rarely solvable exactly, so a large portion of the course will be devoted to simulating or approximating the solution. The master equation and Markov process will be studied in detail in chapter 3. Okay, so so that's basically the overarching route we'll be taking. Okay, so that's basically here where we look at the logical path. Okay, we want to know how exactly each step is done throughout the series. Okay, and if we have time, if I still have time, if I don't, I basically right now I have some loose ends need to wrap up, and that's the main problem. I wish to cover to Fokker-Planck equation and more structured videos, more. I mean, I do believe this is live stream is structured, but it's just more expanded discussion, right? There's viewer interaction, but more condensed version really. Condensed version of these live stream will be made into videos. So, and be added to the stochastic series. So that's it for today. So tomorrow there won't be any of this stuff, but tomorrow instead we'll do the measure theory, weekly measure theory, and on Wednesday we will continue. Okay. Wednesday. Thursday. The thing is, I can do 2 sessions on Friday, but on the other day is only 1. Okay, if at all, lesson or equal to 1. Okay. All right. So that's it for today. Thank you very much for watching, and I'll see you next time. Bye.